Nothing. It's a word we use daily, yet its true meaning eludes us. What exactly is nothing? Can it exist? And if it can, what is it made of? Join us today as we prepare to have your understanding of everything and nothing transformed. Nothing, in a scientific context, is often defined as the absence of matter or the complete lack of anything that possesses mass or volume. This concept can be more complex than it appears, particularly in fields like cosmology and quantum physics. In everyday terms, we might think of nothing as an empty space, but scientists have discovered that what we perceive as empty space still has properties and behaviors that defy our intuitive understanding. One intriguing aspect of this definition comes from quantum physics, where it is suggested that even in a vacuum, which we might consider nothing, there are still fluctuations and virtual particles popping in and out of existence. This means that true nothingness may never be fully realized. There are always underlying fields and energy exchanges occurring at the quantum level. This revelation challenges our traditional conceptions of emptiness. Cosmologically, the idea of nothing extends to the universe itself. The Big Bang theory posits that everything we see today originated from a singular point, often described as a state of nothingness. However, this nothing was not simply empty, but a densely packed point with high energy, eventually leading to the expansion of the universe. The nuances of nothingness raise profound questions about the origins of existence. Moreover, discussions about nothing intersect with philosophical inquiries, contemplating whether true nothingness can exist. These explorations bridge science and philosophy, illustrating that the more we investigate nothing, the more we realize it is woven with complexity. The sheer richness of this concept highlights the limits of our understanding, inviting us to ponder the very foundations of reality. Physicists differentiate between empty space and true nothingness by examining the properties and characteristics associated with each. Empty space, often referred to as a vacuum, appears devoid of matter, yet it is laden with fundamental forces, energy fluctuations, and even virtual particles that momentarily emerge and vanish. This means that what we perceive as a void is far from lifeless. It is a dynamical arena where quantum events occur, influencing the behavior of matter and energy around us. Contrastingly, true nothingness would imply a complete absence of everything. No matter, no energy, no forces, and no space-time itself. In current scientific understanding, such a state is elusive and possibly non-existent. The very fabric of our universe is interwoven with a complex framework of quantum fields, suggesting that the concept of absolute nothing is more philosophical than physical. Even the most expansive vacuums still adhere to laws of physics, retaining properties such as gravitational influence and energy. Additionally, physicists utilize devices like particle accelerators to probe the nature of empty space. When particles collide at high energies, they can create ephemeral particles from the vacuum, showcasing that even what appears to be empty is rich in energy and capable of producing matter under the right conditions. This phenomenon reinforces the idea that empty space is teeming with potential, contrasting sharply with the idea of true nothingness, where such activity would be impossible. The distinctions become even more profound in the context of cosmology. When contemplating the universe's origins, scientists argue that the Big Bang did not emerge from nothing in the true sense, but rather from an extremely hot and dense state that could be misinterpreted as nothingness. Thus, the boundaries between empty space and true nothingness lie not only in observable properties, but also in deeper theoretical implications, making the exploration of these concepts a fascinating journey into the cosmos. The concept of absolute nothingness existing within our universe poses profound questions that touch on both physics and philosophy. In the context of our universe, absolute nothingness would mean the complete absence of matter, energy, space, and time. However, current understanding suggests that such a state may not be possible within the framework of quantum mechanics and cosmology. According to quantum field theory, even what we consider to be a perfect vacuum is not completely empty. Instead, it is filled with quantum fields that result in persistent fluctuations. These fluctuations give rise to virtual particles that transiently emerge from the vacuum, indicating that empty space is, in fact, an active participant in the dynamics of the universe. This phenomenon suggests that even if matter were to be removed, the underlying quantum fields would still exist, preventing true nothingness from arising. In cosmology, the origins of our universe are attributed to the Big Bang, which originated from an extremely hot and dense state. This implies that before this event, the concept of absolute nothingness may not have applied. Rather than emerging from nothing, the universe's inception involved various forms of energy and fundamental particles compressed into a single point. Therefore, the existence of any state resembling absolute nothingness seems incompatible with the known principles of physics governing the universe. Furthermore, the philosophical implications of absolute nothingness raise additional challenges. If true nothingness were to exist, it would lack the basic elements necessary for observation or interaction, making it nearly impossible to conceptualize within the scientific framework. Thus, while it is fascinating to ponder, our current understanding suggests that absolute nothingness is an abstract idea rather than a realizable state within the universe we inhabit. This exploration invites continual inquiry into the nature of existence and the structures that form the reality we experience. The concept of nothingness has undergone significant evolution throughout scientific history, reflecting deeper understandings of the universe and our place within it. In ancient philosophy, thinkers like Aristotle grappled with the notion of nothing as an idea of absence. He famously rejected the idea of a void, positing that nature abhors a vacuum and that something cannot come from nothing. Such views dominated for centuries, shaping early scientific and philosophical thought. As science progressed, particularly during the Enlightenment and the emergence of modern physics, the understanding of nothingness began to shift. Isaac Newton's laws of motion and universal gravitation suggested a universe filled with matter and forces, reinforcing the notion of a tangible, filled space. However, Newton's universe also opened the door to considering what lay beyond observable matter, although pure emptiness was still not thoroughly explored. The advent of quantum mechanics in the early 20th century brought revolutionary changes to the concept of nothingness. With the discovery of quantum fluctuations, scientists found that even empty space is alive with activity. The vacuum state, once thought to be devoid of anything, is understood to contain fluctuating energy levels and virtual particles. This realization fundamentally altered the view of nothingness. No longer could it be considered simply as an absence, but rather as a dynamic entity with its own properties. In contemporary cosmology, the understanding of nothingness has further matured through insights gained from the Big Bang theory. Here, the early universe is viewed not as an empty void, but as an extraordinarily dense and hot singularity brimming with potential. Recent theories about dark energy and the structure of spacetime continue to challenge and refine the definition of nothingness. The evolution of this concept reflects a continual quest for knowledge about the universe, revealing that nothingness is intricately tied to existence and the very laws of physics defining our reality. The concept of zero plays a crucial role in understanding nothingness, particularly in mathematics and physics. At its core, zero represents the absence of quantity, the point at which there is nothing to count. This foundational idea allows scientists and mathematicians to express the concept of nothingness in a way that can be systematically analyzed and manipulated. In doing so, zero becomes a powerful tool for delineating absence from presence, bridging the gap between concepts that might seem purely philosophical and those that are rigorously scientific. In mathematics, zero is not merely a placeholder. It is an essential element in arithmetic and algebra. It facilitates operations that involve the idea of nothingness, enabling equations to express balance and equivalence. For example, in the equation representing equilibrium, the left and right sides may sum to zero, demonstrating how zero can signify a state of rest. By offering a numerical representation of nothingness, zero allows for clearer definitions and explorations of existence itself. Within physics, zero takes on even more profound implications. When describing states of energy, temperature, or movement, A value of 0 can often indicate a lack of activity or presence. For instance, absolute 0 refers to a theoretical state in which molecular motion ceases entirely. Such concepts highlight how 0 helps us recognize boundaries between states of being and non-being, shaping our understanding of the universe's laws and behaviors. Moreover, as discussions around quantum mechanics have revealed, even in a vacuum state where nothing seems to exist, the number of particles or energy can still fluctuate around 0. Thus, the interplay of 0 and nothingness serves as a reminder that absence itself is inherently tied to presence. The concept of 0 thus underscores the intricate relationship between nothingness and existence, demonstrating that even the absence of something carries substantial meaning in scientific inquiry. Different cultures have varied perspectives on the concept of nothingness, often shaped by their philosophical, spiritual, and scientific traditions. In Eastern philosophies such as Buddhism, nothingness is often associated with the concept of emptiness or sunyata. This idea denotes not just the absence of being, but rather a deeper understanding of the interconnectedness of all things and the impermanence of existence. Emptiness in this context is not something to be feared. Instead, it is seen as an opportunity for enlightenment and realizing the true nature of reality, where notions of self and identity dissolve. In contrast, ancient Greek philosophy approached nothingness more with skepticism. Thinkers like Parmenides questioned the very notion of nothingness, asserting that nothing comes from nothing. For them, being was the primary reality, and any conception of nothingness was often viewed as a paradox or an idea that could lead to confusion. This skepticism carried over into later Western philosophies, where nothingness was often grappling with ideas of existence and non-existence. The discussions around the void and existentialism, especially in the works of philosophers like Jean-Paul Sartre, highlighted the existential dread associated with nothingness and the search for meaning within it. Indigenous cultures have unique interpretations of emptiness and nothingness, often integrating these concepts into their cosmologies. Many Native American philosophies, for instance, express a harmonious relationship with nature, wherein the absence of material possessions or the emptiness found in nature is viewed positively. Emptiness can signify a space for potential, creation, and regeneration, emphasizing the cycle of life rather than a finality of absence. In contemporary thought, particularly in the field of art, literature, and psychology, nothingness is often explored as a thematic element, representing aspects of hope, despair, or potential. Whether depicted in literature's exploration of existential themes or in art's abstract representations, the cultural perception of nothingness continues to evolve. This reveals a rich tapestry of interpretations that reflect the values, existential attitudes, and spiritual beliefs of various societies, highlighting that the quest to understand nothingness is as diverse as humanity itself. The quantum vacuum is a fundamental concept within quantum field theory, often described as the lowest energy state of a field, where no particles are present. However, this understanding can be quite misleading if we equate the quantum vacuum with the notion of nothingness. Although it may appear empty, the quantum vacuum is anything but devoid of activity. It teems with dynamic fluctuations and a myriad of virtual particles that pop in and out of existence, giving rise to a constantly changing backdrop of energy. These quantum fluctuations challenge the traditional idea of nothingness. In a classical sense, nothing might be thought of as an absolute void, but the quantum vacuum reveals that even this emptiness is profoundly rich. The vacuum has intrinsic properties, such as vacuum energy, which can influence physical phenomena. For example, the Casimir effect demonstrates how vacuum fluctuations can lead to observable forces between objects placed very close together, essentially proving that empty space is loaded with energy. The relationship between the quantum vacuum and nothingness also emerges in discussions about the origins of the universe. Many cosmological models posit that the universe originated from a state associated with vacuum energy. While the quantum vacuum might be void of matter, its energy content suggests a potential for creation and change, prompting consideration of whether true nothingness could ever exist. In this light, the quantum vacuum implies that the very concept of nothingness may be more nuanced and complex than simply the lack of anything substantial. Thus, rather than serving as true nothingness, the quantum vacuum underscores the idea that what we perceive as absence is a vibrant state full of dynamic possibilities. The discoveries of quantum mechanics highlight how our understanding of nothingness is evolving, demonstrating that even the emptiest of spaces contains the seeds of existence. The exploration of the quantum vacuum continues to redefine our perception of reality, blurring the lines between being and non-being. Virtual particles represent a significant challenge to our traditional understanding of empty space by demonstrating that what we perceive as a void is actually a seething mass of activity at the quantum level. According to quantum field theory, virtual particles are temporary fluctuations that occur in the quantum vacuum, emerging and disappearing in incredibly short time frames. These particles are never directly observable, yet their effects can be measured, proving that empty space is not static or devoid of substance. The existence of virtual particles fundamentally alters our conception of empty space. Instead of being a lifeless vacuum, it is more accurately described as a dynamic arena where energy fluctuations occur continuously. These fluctuations allow virtual particles to act as messengers of forces, influencing interactions between real particles. For example, in quantum electrodynamics, virtual particles facilitate electromagnetic interactions by mediating forces between charged particles like electrons. This showcases that empty space is rich with potential, wherein interactions are constantly occurring, even if they remain hidden from direct observation. One of the most striking implications of virtual particles is the casimir effect, which illustrates how two uncharged parallel plates can experience an attractive force due to the restriction of virtual particles between them. This phenomenon serves as empirical evidence that empty space can exert real forces and influence physical objects, providing tangible proof that our understanding of vacuum, as a mere absence of matter, is incomplete. Moreover, the concept of virtual particles also invites us to rethink fundamental questions about the nature of reality. They challenge the notion that existence strictly relies on observable entities by revealing that much of the universe's behavior occurs beyond traditional measurements. Virtual particles highlight the incredible complexity of quantum mechanics and emphasize that empty space is fundamentally interconnected with the workings of the universe, reshaping our understanding of both space and the fabric of reality itself. The casimir effect is significant in relation to nothingness because it provides tangible evidence that what we perceive as empty space is far from being an absolute void. Discovered in the mid-20th century by physicist Hendrik Casimir, this phenomenon occurs when two uncharged parallel plates are placed very close together in a vacuum. Surprisingly, these plates experience an attractive force that pulls them toward each other, a result of the fluctuations of virtual particles in the quantum vacuum. This effect illustrates that even in what we define as emptiness, there is a vast energy field at play. The vacuum between the plates restricts the types of virtual particles that can exist, leading to a difference in energy density on either side of the plates. Consequently, the energy from the quantum vacuum pushes them together, revealing that empty space has properties and behaviors that challenge our conventional understanding of nothingness. The Casimir effect shows that nothing is not inert or passive. Instead, it is filled with the potential for interactions that can have observable consequences. Furthermore, the Casimir effect has implications for theoretical physics that extend beyond a simple understanding of nothingness. It highlights the inherent complexities of the quantum vacuum and urges scientists to reconsider the dynamics of space itself. This realization expands the definition of nothingness from an absolute absence to a realm of possibilities, where fluctuations and virtual entities can produce measurable effects. In a broader philosophical context, the significance of the Casimir effect invites reflection on the nature of existence itself. It compels us to recognize that even in our most profound contemplations of nothingness, we uncover layers of complexity and activity. Thus, the Casimir effect serves as a striking reminder that the universe operates in ways that often defy our intuitions, urging us to reconsider the boundaries between existence and non-existence. The presence of dark energy profoundly impacts our understanding of empty space by introducing a dynamic form of energy that permeates throughout the universe. Discovered through observations of the accelerated expansion of the universe, dark energy comprises about 70% of the universe's total energy content. Contrary to our traditional notion of empty space as a mere void, dark energy suggests that it is an active participant in the cosmic landscape, contributing to the overall behavior of the universe and its expansion. One of the most intriguing aspects of dark energy is that it appears to exert a repulsive force, working against the attractive pull of gravity. This imbalance accelerates the expansion of the universe, which challenges earlier models that depicted a static or gradually slowing cosmos. As it stands, dark energy offers a mechanism by which seemingly empty space can foster rapid cosmic growth. Instead of being a passive void, empty space is revealed as a complicated mixture of energetic properties that influence the fabric of the universe. Additionally, dark energy's influence on empty space raises important questions about the nature of the vacuum itself. In the context of quantum field theory and the quantum vacuum, understanding dark energy reveals potential connections between vacuum energy and the observed acceleration of cosmic expansion. While quantum fluctuations characterize empty space, dark energy introduces an inherent energy density that affects the universe on large scales, indicating that our perception of nothingness must incorporate these active forces. This evolving understanding of empty space, shaped by the presence of dark energy, challenges us to rethink foundational concepts in cosmology. Rather than regarding the universe as a static stage on which events unfold, we see that space itself is dynamic and constantly influenced by forces we are only beginning to comprehend. The interplay between dark energy and empty space illuminates the deeper complexities of the universe, inviting ongoing inquiry into both the nature of existence and the fabric of reality itself. Attempting to visualize or conceptualize true nothingness is inherently challenging, as our minds are conditioned to think in terms of existence and tangible experiences. One approach is to consider nothingness as a fundamental absence, a complete lack of matter, energy, space, and time. However, this definition can quickly become abstract and elude our understanding, as even the absence of anything can still evoke questions about how we perceive reality. One way to approach this visualization is through analogy and abstraction. Imagine a perfect void, an emptiness without light, sound, or any form of physical presence. This can be akin to the concept of absolute darkness, where even the faintest glimmer of light or color is absent. In this state, our usual sensory perceptions fail to apply, leading us to confront a conceptual space devoid of any characteristics we typically associate with being. Philosophical explorations also play a vital role in comprehending nothingness. Thinkers like Martin Heidegger and Jean-Paul Sartre examined the existential implications of nothingness, often illustrating how it relates to human experience. In these discussions, nothingness might be linked to ideas of emptiness in existence or the void that arises in moments of profound reflection. Such concepts hint at nothingness as a profound state rather than a mere absence, suggesting that, paradoxically, it can illuminate our understanding of what it means to exist. Additionally, visualizing nothingness can involve contemplating the boundaries of our universe. The observable universe has limitations, and when we think about what exists beyond these boundaries, we encounter the idea of incomprehensible emptiness. However, even this conceptualization remains intertwined with our ideas of space-time and energy. Ultimately, engaging with true nothingness leads to the recognition that our cognitive frameworks are deeply rooted in the phenomena of existence, making absolute nothingness a conceptual challenge that invites us to explore the unknown. Engaging in mental exercises can help to approach the difficult concept of absolute void by promoting abstract thinking and challenging our conventional perceptions of existence. One effective exercise is the thought experiment of emptying the mind. This involves finding a quiet space and practicing meditation or mindfulness to consciously let go of sensory input and internal dialogue. By allowing thoughts to fade and focusing purely on a state of mental silence, participants can begin to sense a level of emptiness that may mirror the characteristics of an absolute void. Another exercise is visualizing layers of existence. Start by imagining the physical elements surrounding you, including objects, people, and the environment. Gradually strip away these layers, picturing each element disappearing one by one, first the people, then the objects, and finally, the familiar sounds. As you continue this exercise, strive to reach a point where you perceive a vast emptiness. Rather than feeling distress, this visualization can foster a sense of openness to the idea of an unfilled space, inviting reflections on the nature of absence. Additionally, engaging with paradox can be another useful exercise. Consider the idea that defining something as nothing inherently requires the use of language and thought, which are tools grounded in existence. Ponder how an empathetic acknowledgement of nothingness resides within the context of being. By grappling with these contradictions, the mind can cultivate a deeper understanding of the intricate relationship between existence and non-existence. Lastly, consider reading and reflecting on philosophical texts that approach the notion of void or nothingness. Engaging with the writings of thinkers like Martin Heidegger, Jean-Paul Sartre, or Eastern philosophies such as Buddhism can provoke thought and invite exploration into these complex themes. This intellectual exercise encourages the individual to confront and process the abstract attributes of the concept while grappling with profound existential questions. These combined mental exercises create a pathway to approaching absolute void, expanding the mind's capacity to engage with the challenging yet intriguing notion of nothingness. Comprehending complete nothingness is challenging for the human mind due to several factors rooted in our cognitive and sensory experiences. First and foremost, our perceptions are fundamentally anchored in the existence of things. We are creatures of experience, constantly interacting with a world filled with matter, energy, and sensory input. From childhood, we learn to understand the world through these interactions, making it difficult to conceptualize a state devoid of all forms of existence. Our brains are wired to recognize and categorize what is around us, meaning that the idea of nothingness, a complete absence, poses a significant cognitive challenge. Additionally, language plays a crucial role in shaping our thoughts. Most languages are built upon concepts of existence, utilizing words that describe objects, sensations, and experiences. Attempting to articulate or define nothingness often leads to paradoxes, as we find ourselves using terms that inherently relate to something instead of nothing. This linguistic limitation creates a barrier when trying to fully embrace the concept of absolute void, leading to confusion and inconsistency in our understanding. Philosophical inquiries also complicate our relationship with nothingness. Many philosophical traditions explore the nature of existence and non-existence, often arriving at profound questions without clear answers. This exploration confronts individuals with existential dilemmas about meaning, purpose, and the nature of reality, which can be both thought-provoking and unsettling. When faced with the idea of complete nothingness, the mind inherently grapples with deeply rooted fears and uncertainties about the implications of such a state. Finally, the notion of nothingness tends to evoke a sense of existential dread. Confronting the idea that there could be a state completely devoid of life, purpose, or structure invites anxiety and confrontation with our own mortality. This emotional response can further inhibit our ability to engage with the concept intellectually. The combination of these cognitive, linguistic, philosophical, and emotional factors results in a multifaceted challenge for the human mind when it comes to comprehending complete nothingness. Sensory deprivation experiments provide a fascinating lens through which to explore the experience of nothingness, as they specifically aim to isolate individuals from external stimuli. In these experiments, participants are placed in controlled environments, such as flotation tanks or dark, soundproof rooms, where visual and auditory inputs are significantly reduced or eliminated. This environment encourages introspection and alters the participants' perception of reality, often leading to experiences that resonate deeply with the concept of nothingness. As external stimuli diminish, individuals often report heightened awareness of their internal thoughts, emotions, and sensations. The absence of sensory input creates a unique state where the usual distractions of daily life fade away, allowing participants to confront their own minds. This isolation can evoke feelings of profound emptiness, or conversely, an overwhelming flood of thoughts and emotions. Some individuals describe this experience as unsettling, while others may find it liberating, highlighting the diverse interpretations of what nothingness can mean when stripped of external influences. Moreover, sensory deprivation can lead to altered states of consciousness, where time perception, self-identity, and reality often seem to blur. Participants may experience states of deep relaxation, dissociation, or even hallucinations. These phenomena can challenge conventional perceptions of existence and non-existence, as the awareness of one's own consciousness persists even in the absence of external stimuli. In this sense, the experiments serve to illustrate that nothingness is not simply a void, but a complex state that exists alongside consciousness itself. Ultimately, sensory deprivation experiments illuminate the intricate relationship between perception and the concept of nothingness. They demonstrate that the experience of emptiness can evoke a spectrum of emotional and cognitive responses, pushing individuals to confront what it means to exist in the absence of external influences. Through these explorations, participants gain insights into the nature of reality, presence, and the human experience, enriching our understanding of nothingness beyond mere abstraction. Consciousness profoundly shapes our understanding of nothingness. When we confront the concept of nothingness, it is our consciousness that allows us to recognize the absence of things rather than an empty void that lacks any definition at all. This awareness is essential. Without consciousness, we would have no insight into anything, whether that be the presence of objects or the very notion of emptiness itself. Our minds are constantly interpreting sensory information and constructing a reality filled with meanings and sensations. When we think about nothingness, we are tapping into a state defined by the lack of these interpretations. This mental engagement occurs because consciousness enables us to question and reflect on our experiences. We can contemplate a scenario without matter or form, even though such a state is difficult to grasp and perhaps beyond our typical experiences. It is through the lens of consciousness that we can explore and examine the boundaries of existence, framing our understanding in ways that provoke curiosity and deeper philosophical inquiries. Interestingly, concepts of nothingness extend into the realms of physics and cosmology as well. For example, scientists explore the vacuum of space, which is often misperceived as simply empty. In reality, even the emptiest regions of space teem with quantum fluctuations, suggesting potential energy. Here, consciousness allows us to navigate complex theories that challenge our perceptions and broaden our understanding of reality beyond everyday experiences. The interplay between consciousness and nothingness ignites discussions in both scientific and philosophical realms. The ability to conceptualize nothingness illustrates our unique capability to ponder existence itself. Thus, while we may grapple with what nothingness truly entails, it is our conscious experience that grants us the tools to engage with these profound questions, enriching our appreciation of the universe and our place within it. Artists and creators tackle the concept of nothingness in various innovative ways, using their mediums to provoke thought and evoke feelings that relate to absence or void. In visual art, for example, artists often utilize blank canvases or vast empty spaces to symbolize nothingness. This minimalist approach can challenge viewers to confront their thoughts and feelings about emptiness, inviting them to fill the void with their interpretations and emotions. The choice of color, or sometimes the complete lack of it, becomes a powerful statement on absence and the spaces between existence. In literature, themes of nothingness often manifest in existential narratives, where characters grapple with the meaning of life, identity, and the void in between experiences. Authors use language to explore feelings of alienation and desolation, crafting passages that emphasize what is absent. This exploration invites readers to reflect on their own experiences of nothingness, encouraging an introspective journey through the characters' dilemmas and the philosophical questions they pose. The narrative can serve as a mirror, reflecting our own encounters with absence and the search for meaning in a world that often feels hollow. In music, the representation of nothingness can take on an auditory form. Composers might use silence, pauses, or sparse instrumentation to create a sense of emptiness or void. By weaving silence into their compositions, they allow listeners to experience the space between notes, transforming absence into a poignant part of the piece. This engagement with silence creates a profound contrast to sound, highlighting feelings of isolation or contemplation, further deepening the listener's emotional connection to the concept of nothingness. The interpretations of nothingness in art, literature, and music often connect on a deeper level, transcending traditional boundaries and inviting audiences to explore the complexities of existence. By grappling with nothingness, creators challenge us to confront uncomfortable truths and develop a richer understanding of the human experience, encouraging meaningful reflections on our own lives and the spaces that define them. Mathematics offers intriguing frameworks for examining the concept of nothingness, providing tools that can enhance our understanding of absence and void. One compelling notion is the concept of zero, which in mathematics represents a state of having no quantity. Zero serves as a foundation for numerous mathematical operations, acting not just as a placeholder, but as a pivotal point in various equations. It allows us to explore the transitions between existence and non-existence, illustrating how something can be derived from nothing. In the realm of set theory, the idea of the empty set is another significant mathematical representation of nothingness. The empty set contains no elements, yet it is still acknowledged as a fundamental concept that facilitates discussions about collections and operations within mathematics. This abstraction helps illustrate how nothingness can still hold value and meaning within a mathematical context, emphasizing that even in absence, there is a framework for understanding. Beyond pure mathematics, concepts like fractals demonstrate how complexity can arise from seemingly empty spaces. When examining fractals, one finds infinite patterns emerging from simple geometric principles. This reinforces the idea that nothingness can give rise to infinite possibilities, suggesting that within the void, there exist hidden structures and potentialities waiting to be revealed. Such insights prompt deeper philosophical inquiries into the nature of existence and the cosmos. In physics, theories involving vacuums and quantum mechanics further intertwine with mathematical principles. The vacuum of space is not truly nothing, but instead a dynamic field bursting with activity at the quantum level. Here, mathematical tools allow scientists to describe behaviors of particles and energy that challenge traditional notions of emptiness. By utilizing mathematics, we can better navigate the complexities of nothingness, transforming it from an abstract concept into a subject of real scientific inquiry, ultimately enriching our comprehension of the universe and our place within it. The relationship between nothingness and the philosophical concept of non-existence is profound and complex, often serving as a focal point for deep existential inquiry. Nothingness typically refers to a state or condition devoid of any existing entities, while non-existence leans more toward the idea of something that does not exist or has never existed. This distinction invites philosophical exploration into the nature of reality and the very fabric of existence itself. One significant philosophical approach to nothingness is rooted in existentialism, where thinkers like Jean-Paul Sartre and Martin Heidegger contemplate the implications of nothingness on human awareness and existence. For these philosophers, nothingness is intertwined with freedom and choice. It represents an absence that allows consciousness to question its own significance. This exploration suggests that understanding nothingness can lead individuals to confront the ultimate questions of purpose and meaning as they recognize their existence amid a potentially indifferent universe. Additionally, the philosophical inquiry into non-existence often grapples with ideas about what it means for something to not be. If we consider the concept of non-existence, we must reflect on whether it is possible to fully comprehend something that has never been present. This raises questions about the nature of absence. Does non-existence have any properties, or is it a state that utterly resists comprehension? Philosophy addresses these questions by pushing boundaries, challenging our established notions of reality, perception, and the cosmos. The ideas of nothingness and non-existence are not only abstract concepts, but also provoke fundamental questions about life, our place in the universe, and the parameters of reality. This contemplation is important as it shapes not just philosophical thought, but also influences artistic expression and scientific inquiry. By deeply engaging with nothingness and non-existence, we gain insight into the multifaceted nature of existence itself, prompting us to explore the very essence of being and the void that surrounds it. Dreams and meditative states offer unique insights into the experience of nothingness, allowing individuals glimpses of a reality that transcends ordinary perception. When we dream, especially in the realm of lucid or profound dreams, we can encounter states where familiar boundaries dissolve. The surreal quality of dreams often removes the constraints of time, space, and logic, confronting us with experiences that might feel like stepping into nothingness. This altered state allows us to explore the depths of our consciousness and reflect on the unstructured aspects of our mind, shedding light on the nature of existence and absence. Meditation, on the other hand, is a discipline that intentionally guides individuals towards states of stillness and mindfulness. As practitioners quiet their thoughts and sensations, they can cultivate an experience that resembles nothingness. In these moments of profound calm, feelings of separation from the self and the external world can emerge, leading to a sensation of merging with the void. This state invites practitioners to let go of attachments, desires, and distractions, emphasizing the intrinsic peace that can be found in the absence of thought and the chaos of daily life. Both dreams and meditation can reveal that nothingness is not simply an absence, but also a rich landscape for exploration. These experiences can challenge preconceived notions about presence and absence, inviting deeper connections with our emotions, thoughts, and even the universe itself. In dreams, one might confront fears or unresolved issues, using the lack of structure to understand personal narratives better. Similarly, in meditation, the stillness often leads to profound revelations, expanding one's perspective beyond the usual confines of the mind. Engaging with nothingness through these states cultivates awareness, encourages introspection, and ultimately enhances our understanding of existence. Dreams and meditation become gateways to exploring the vast domains of consciousness, where experiences of emptiness can foster clarity and insight into the interplay between being and non-being. As individuals navigate these dimensions, they may discover that nothingness holds immense potential for growth, understanding, and appreciation of the intricate tapestry of life. Different scientific disciplines approach the visualization of nothingness in fascinating and varied ways, each offering unique perspectives informed by their methodologies and focus areas. In physics, especially in the context of quantum mechanics, scientists grapple with concepts such as the vacuum of space, which is often portrayed as an empty void. However, physicists illustrate that this void is not truly empty. It is a seething mass of energy and particles that pop in and out of existence. Visualizations, often using complex mathematical models, depict fluctuations in energy that challenge traditional views of nothingness, transforming it into an active and dynamic field. In cosmology, scientists delve into the vastness of space, attempting to visualize the cosmic background radiation that permeates the universe. This radiation serves as a remnant of the Big Bang and is a fascinating example of how something can emerge from a state that might seem like nothing. By employing detailed simulations and images of the universe's evolution, cosmologists present a view of nothingness that is rich with potential. These visualizations are vital for comprehending how the universe developed from an initial state of extremely high density and temperature to the expansive cosmos we observe today. Philosophy of science also intersects with these discussions, as philosophers reflect on the implications of scientific findings related to nothingness. They often propose thought experiments intended to stretch our understanding of absence. Visual tools used in philosophical inquiries might include diagrams or conceptual models that seek to bridge the gap between abstract theories and tangible experiences. Such visualizations encourage deeper reflection on the nature of existence and what it means to consider something as devoid of being. In the field of psychology, visualization techniques are utilized in therapy to explore concepts of emptiness or void within an individual's mental landscape. Therapists may guide clients in visualizing feelings of nothingness as a way to process emotions or confront anxieties. Through these techniques, nothingness is rendered into a more relatable and tangible experience, facilitating introspection and healing. The intersection of these disciplines highlights that while nothingness may initially seem abstract, there are myriad ways of visualizing and understanding it that speak to both scientific inquiry and human experience. The Big Bounce is a theoretical cosmological model that posits a cyclical nature of the universe, suggesting that instead of a singular beginning, the current universe is the result of a contraction of a previous universe followed by a subsequent expansion. This contrasts sharply with the traditional Big Bang theory, which describes a singular event approximately 13.8 billion years ago when the universe rapidly expanded from an extremely dense and hot state. The Big Bounce introduces the idea that the universe undergoes periodic expansions and contractions, implying that it may have existed in different forms infinitely in the past and will continue to do so in the future. One of the central challenges the Big Bounce presents to the Big Bang theory is its approach to addressing the origins of the universe. The Big Bang theory leaves questions about what occurred before this singular event, as time itself is thought to have begun with the expansion. In contrast, the Big Bounce offers a more dynamic history, suggesting that the universe's expansion follows a contraction phase. This notion helps to circumvent some of the philosophical and scientific dilemmas regarding the absolute beginning of everything, proposing a universe that is eternally cycling through phases of collapse and rebirth. Additionally, the Big Bounce is informed by developments in quantum gravity and string theory. These areas of theoretical physics attempt to reconcile the principles of general relativity, which governs large-scale structures, with quantum mechanics, which rules the microscopic world. According to some models, including loop quantum gravity, the collapsing universe reaches an incredibly high density before undergoing a bounce, leading to a new phase of expansion. This alteration in paradigm could offer insights into phenomena observed at cosmic scales, addressing questions related to the fate of the universe and the singularities predicted by the classical Big Bang model. The concept of the Big Bounce continues to inspire debate and research within cosmology, challenging fully accepted understandings of the universe's inception and evolution. It invites scientists to reconsider the implications of current models while exploring the myriad possibilities for the universe's past and future. This ongoing investigation reflects the dynamic nature of scientific inquiry, illustrating how new theories can reshape our understanding of fundamental questions about existence itself. The theory of eternal inflation offers a compelling framework for understanding the state preceding our universe. According to this model, the universe experienced a rapid expansion called inflation, which occurred just after the Big Bang. However, unlike traditional models that suggest a singular event, eternal inflation posits that this inflationary process is ongoing in different regions of a vast multiverse. In this scenario, while our local universe underwent a tremendous expansion that cooled and settled into the cosmos we observe today, other regions continuously inflate, creating a tapestry of universes, each with potentially different physical laws and constants. At its core, eternal inflation suggests that the very fabric of space-time is eternally undergoing fluctuations, resulting in bubbles of space where inflation ceases and traditional cosmic evolution occurs, like the formation of galaxies and stars. Our universe is just one of countless bubbles that have formed from this persistent inflationary process. Before our universe took shape, conditions were dominated by a chaotic state characterized by rapid expansion and high energy densities, with quantum fluctuations giving rise to the seeds of structures seen today. One of the most intriguing implications of eternal inflation is that it may offer a solution to some of the unresolved questions of cosmology, particularly about the initial conditions of our universe. This theory implies that the pre-universe state is not necessarily a singular point, but rather a complex landscape filled with potential. Within this context, causality is extended beyond our observable universe, as events happening in distant inflating regions may influence the cosmic background in subtle ways. Eternal inflation also introduces the idea of a multiverse, where each bubble, including our universe, might have different characteristics. This possibility prompts philosophical inquiries about the nature of existence and the very concept of our universe as just one manifestation among many. Overall, the theory of eternal inflation redefines how we perceive the beginnings of our universe by placing it within a much larger, ever-evolving context that continues to spark scientific curiosity and inquiry. The no-boundary proposal, introduced by the renowned physicist Stephen Hawking and his colleague Jim Hartle, presents a fascinating perspective on the origins of the universe. This model seeks to address the question of what happened at the very beginning of the cosmos by proposing that the universe does not have any boundaries, either in space or time. According to this idea, the universe can be thought of as the surface of a sphere, where the concept of before the Big Bang becomes meaningless, as time itself does not have a defined starting point in the traditional sense. The essence of the no-boundary proposal lies in the notion that the universe emerged from a quantum state devoid of classical properties. In this framework, instead of starting from a singularity, an infinitely dense point, Hawking and Hartle suggest that the universe began in a smooth, finite state. This state is characterized by a no-boundary condition, where the laws of physics as we understand them break down. The proposal employs the principles of quantum mechanics combined with general relativity, showcasing that the beginnings of the universe can be described using the mathematics of complex geometrical structures known as Wheeler-DeWitt equations. In practical terms, the no-boundary proposal implies that while we can observe and measure our universe, its initial conditions were shaped by quantum fluctuations that yield an infinite diversity of possible outcomes. The universe's history unfolds from this initial state, smoothing out as it expands and evolves according to physical laws. By reconceptualizing the universe in this manner, the model suggests a way to sidestep complicated questions about what preceded the Big Bang and how time functions at the very edge of the cosmos. This groundbreaking theory has significant implications for how we understand our universe's origin and structure. It invites a rethinking of classical notions about space and time, suggesting that rather than starting from a chaotic singularity, the universe blossoms from a quantum landscape where boundaries and origins blur. The no-boundary proposal continues to influence both cosmological research and philosophical inquiries surrounding the nature of existence, showcasing the innovative spirit of modern theoretical physics. String theory offers a unique and complex framework for understanding the pre-Big Bang state of the universe by suggesting that the fundamental building blocks of reality are not point-like particles, but rather one-dimensional objects called strings. According to string theory, these strings vibrate at different frequencies, giving rise to the various particles and forces observed in nature. This theoretical structure has profound implications for cosmology and the exploration of the universe's origins. In the context of pre-Big Bang scenarios, string theory posits that our universe may be just one of many within a larger multidimensional space known as the bulk. Before the onset of what we recognize as the Big Bang, string theory allows for a framework where strings could have existed in a different state. Some models suggest that before the Big Bang, the universe could have been in a highly energetic and dense condition, often referred to as a string gas state, where numerous strings interacted in complex ways. This state could lead to the emergence of our universe as one bubble among many, formed from the vibrational modes of strings settling into a more stable configuration. Furthermore, string theory incorporates concepts like brain world scenarios, where our universe is a three-dimensional brain embedded in a higher dimensional space. In this model, events on the brain, including the Big Bang, could have been triggered by collisions with other brains or interactions within the bulk. Such collisions could provide the necessary energy for our universe to expand, creating a dramatic transition from a pre-Big Bang state into the universe we currently inhabit. String theory thus challenges conventional understandings of cosmology by suggesting that the Big Bang may not be a singular, definitive beginning, but rather part of a continuous cycle of interactions among strings and brains in a higher dimensional space. This perspective encourages a re-evaluation of what we consider the origins of the universe, positioning the Big Bang as a transition from a prior state defined by string dynamics. Although still largely theoretical and mathematically intricate, string theory expands the horizons of cosmological inquiry, leading to exciting possibilities regarding the nature of existence both before and after the Big Bang. The cyclic model of the universe, proposed by physicists Paul Steinhardt and Neil Turok, presents a fascinating alternative to traditional cosmological models that posit a singular beginning. According to this innovative theory, the universe undergoes an eternal sequence of expansions and contractions, with each cycle consisting of a Big Bang-like phase followed by a gradual expansion, ultimately leading to another contraction and the next Big Bang. This model emphasizes that rather than being a one-time event, our universe is part of an ongoing cycle of rebirth, presenting a dynamic perspective on cosmic evolution. At the heart of the cyclic model is the idea that the universe consists of higher dimensional branes influenced by ideas from string theory. In this framework, our three-dimensional universe is viewed as a brane that periodically collides with another brane, triggering a bounce or a new phase of expansion. Each collision results in a dramatic release of energy akin to a Big Bang, initiating a new cycle. The key component of this model is that these interactions can continue indefinitely, allowing for a universe that is ageless and continually evolving. One significant advantage of the cyclic model is its capacity to address some of the unresolved questions posed by traditional cosmological theories, including the apparent fine-tuning of the universe and its current accelerating expansion. By incorporating elements from the realms of quantum physics and cosmology, Steinhardt and Turok provide a mechanism for resolving such issues through the dynamics of the cyclic process. For example, the processes occurring during the contraction phase could help smooth out irregularities and set the stage for fresh cycles, imparting a sense of self-regulation to the universe's evolution. The implications of the cyclic model extend beyond cosmology to also engage with philosophical questions regarding time and existence. By suggesting that the universe experiences an infinite series of cycles, this theory proposes a view of cosmic history that transcends conventional narratives tied to singular beginnings. Although the idea remains under scientific scrutiny, it opens intriguing avenues for inquiry into the nature of time, the origins of our universe, and how physical laws might govern the grand cyclical dance of creation and destruction on a cosmic scale. Loop quantum cosmology offers a distinctive perspective on the state preceding the Big Bang by applying principles derived from loop quantum gravity, a theoretical framework that seeks to unify general relativity and quantum mechanics. This approach fundamentally alters our understanding of the universe's beginnings, suggesting that the structure of spacetime itself features discrete, quantized properties rather than being a continuous entity. In this view, the universe may have undergone a significant transition rather than a singular beginning at the Big Bang. Prior to the Big Bang, loop quantum cosmology posits that the universe was in a highly dense state characterized by quantum fluctuations. As the universe approached this critical state, it transitioned through what is termed a quantum bounce. Instead of encountering a singularity where density becomes infinite and the usual laws of physics break down, the framework suggests that the universe contracts and then rebounds. In this model, gravity plays a crucial role, as the quantization of spacetime prevents the formation of singularities that plague traditional cosmological models. The implications of this approach are profound. Instead of the Big Bang serving as the absolute beginning of time and space, loop quantum cosmology allows for the idea that the universe may have existed in a prior state characterized by contraction. The bounce then represents a transition into the expansion we currently observe. This model helps resolve some of the philosophical dilemmas surrounding the nature of time, as it implies that time can extend beyond the Big Bang and that new cycles of expansion could potentially emerge from earlier collapses. Loop quantum cosmology not only addresses the challenging issues of singularities, but also provides a framework for analyzing the early universe's dynamics. By emphasizing the quantum nature of spacetime, this approach enables scientists to explore how the universe evolved through various phases, potentially leading to new insights about its overall structure and longevity. This exciting avenue in theoretical physics continues to inspire research and debate, offering a captivating look at the fundamental nature of our universe and the events that shaped its origins. The ekpyrotic universe theory presents a novel cosmological model that directly challenges conventional understandings of the Big Bang. This theory, introduced by theorists including Paul Steinhardt and Neil Turok, posits that the universe's evolution originated from the collision of two three-dimensional branes in a higher dimensional space. Rather than envisioning the Big Bang as a singular explosive event, the ekpyrotic model suggests that our universe was birthed from the energy and dynamics of this collision, marking a transition from a prior state defined by the interactions between these branes. In this context, the pre-Big Bang state is characterized not by nothingness or a singularity, but by a preceding existence of physical structures and energy within the higher dimensional space. Before the collision, the branes could have been in close proximity, with their dynamics influencing the fabric of space-time in ways that would impact what we observe in our universe today. The collision itself generates the hot, dense conditions that align with characteristics expected of the early universe, effectively showing how our Big Bang is a natural outcome of these interactions rather than a unique and isolated event. One key feature of the ekpyrotic model is its ability to mitigate some of the issues associated with traditional Big Bang theory, including the flatness and horizon problems. By emphasizing a more gradual transition from one state to another, the theory offers an alternative mechanism for structure formation, suggesting that density fluctuations can arise from quantum perturbations occurring in the pre-collision environment. This shifts the focus from explosive expansion to a more nuanced understanding of the cosmos, where interactions in higher dimensions lay the groundwork for the observable universe. The ekpyrotic universe theory emphasizes a cyclical nature reminiscent of other cyclic models, as it allows for the possibility of multiple collisions and, consequently, multiple universes. This vision reshapes not just our understanding of cosmic origins, but also the nature of existence itself, prompting thought on how interconnected forces in higher dimensions may govern the boundaries of our own universe. Ultimately, the ekpyrotic model encourages a fresh perspective on the pre-Big Bang state by integrating ideas from string theory and brane cosmology, blending them into a cohesive framework that expands our comprehension of the cosmos. The concept of a multiverse introduces the idea that our universe may be just one of many universes existing simultaneously in a vast, interconnected framework. This notion can significantly reshape our understanding of what might have existed before our universe, providing a broader context for exploring cosmological origins. Several theoretical frameworks, such as inflationary cosmology, string theory, and the ekpyrotic model, propose different forms of multiverses, each with unique implications for pre-Big Bang states. In the context of inflationary cosmology, the multiverse arises from the idea that different regions of space can undergo inflation at different rates, leading to pocket or bubble universes. Each bubble corresponds to distinct physical characteristics, potentially governed by different laws of physics. Before our universe came into being, it might have originated from an inflating field that decayed, producing a particular bubble while leaving vast stretches of inflating space around it. This infinite sea of inflation could imply that numerous other universes exist, some similar to ours and others radically different, each emerging from their unique conditions and quantum fluctuations. In string theory, the multiverse concept can manifest through different configurations of branes and dimensions. The interactions between these branes could give rise to various universes, each encapsulating different physical properties. The pre-Big Bang state, therefore, may not simply precede our universe, but exist amid an expanse of other cosmos, all intertwined yet separate. This would suggest that existence extends beyond our comprehension, incorporating myriad forms of reality that defy conventional boundaries. Moreover, the ekpyrotic model also supports the multiverse hypothesis, as it envisions a universe born from the collision of branes in higher dimensions. Each of these collisions can lead to the formation of diverse universes, creating a scenario where what we consider to be the singular Big Bang is merely a localized event within a broader multiverse structure. The idea of a multiverse encourages a rethinking of traditional cosmological narratives, as it presents multiple avenues for understanding both the origins of our universe and the nature of existence itself. While challenging to empirically test, the multiverse concept invites deeper philosophical reflections on reality, prompting us to consider the boundaries between universes, the nature of time and space, and what it truly means to exist within an ever-expanding cosmos of possibilities. Conformal cyclic cosmology, proposed by renowned physicist Roger Penrose, presents a compelling alternative perspective on the universe's evolution and the nature of cosmic time. This theory suggests that the universe undergoes an infinite series of cycles, where each cycle is referred to as an eon. Unlike traditional models that view the Big Bang as a singular event marking the universe's beginning, conformal cyclic cosmology posits that each eon evolves from the remnants of the previous one, facilitating a continuous process of rebirth. The key to understanding this model lies in the concept of conformality. Penrose argues that as the universe ages and expands, its structure becomes increasingly simpler, with matter and energy dissipating and rendering it closer to a uniform state. In this highly expanded, low-energy condition, the distinct properties of time and space begin to lose their traditional meaning. Penrose asserts that at this juncture, the universe can be mathematically transformed into a new eon through a process of conformal mapping. This transformation blends the end of one eon seamlessly into the beginning of another, maintaining the fundamental structure of space-time while erasing the features that distinguish previous cycles. This framework allows for a universe that is eternal and evolves without requiring a singular origin point as traditionally defined. It emphasizes that the Big Bang is not an absolute beginning, but rather a transitional phase that arises from the end stages of a prior universe. The transitions between eons can be seen as a smoothing out of complexity, where the remnants of previous cosmic structures contribute to the new cycle without retaining any memory or distinct characteristics. Penrose's conformal cyclic cosmology offers compelling insights into questions about the nature of time, existence, and the fate of the universe. While the theory remains controversial and subject to debate within the scientific community, it provides a novel view that challenges conventional narratives, suggesting that the universe is engaged in an endless dance of cycles, each one leading to the next, blurring the lines between beginnings and ends. By encouraging fresh perspectives on cosmology, Penrose's model fosters profound inquiries into the nature of reality itself and our understanding of the cosmos across infinite scales of time. The chaotic inflation theory presents a fascinating perspective on the state of our universe prior to what we can currently observe. According to this theory, before the Big Bang and the subsequent expansion that led to our observable universe, there existed a vast expanse of space filled with energy, undergoing rapid fluctuations. This realm was characterized by an inflationary phase that could have begun in a multitude of ways, leading to different pockets of inflation, each potentially developing into separate universes or bubbles. In this scenario, the chaotic inflation theory suggests that the conditions were not uniform. Instead, variations in energy density created regions that inflated at different rates. This means that while one region might have transitioned into the familiar universe we inhabit, nearby areas may not have experienced the same fate, resulting in an incredibly diverse multiverse. Each of these universes could feature unique physical laws and constants, highlighting the randomness of cosmic processes. Surprisingly, the universe we observe now, with its galaxies, stars, and planets, is only a small part of a far larger and more complex reality. The chaotic inflation theory encourages us to reconsider our place in the cosmos, as it implies that our universe is simply one manifestation in a potentially infinite expanse of diverse realities. This idea of multiple universes challenges our understanding and evokes profound questions about the nature of existence itself. Through chaotic inflation, we gain insights into the early moments before our universe took shape, emphasizing the chaotic and unpredictable forces that shaped the cosmos. This theory not only deepens our understanding of cosmic evolution, but also invites us to ponder the mystery of what lies beyond the limits of our observable universe, sparking curiosity about the nature of reality itself. The notion of time before the Big Bang is one of the most compelling and perplexing puzzles in cosmology. According to the standard model of the Big Bang theory, time and space originated simultaneously at the moment of the Big Bang, approximately 13.8 billion years ago. This suggests that asking what happened before this event may be fundamentally flawed, as time as we understand it did not exist prior to the Big Bang. Essentially, the Big Bang marks the beginning of time itself. Some physicists theorize the existence of a timeless state, or a phase where traditional concepts of time are not applicable. In such a scenario, events as we know them could not take place because the very framework of temporal progression was absent. Discussions surrounding this period often lead to the exploration of alternative timelines or conditions of existence, where the rules that govern our universe might not have applied. Other theories explore the potential for a cyclic universe, where the universe undergoes endless expansions and contractions. Under this model, the Big Bang does not mark a definitive beginning, but rather a transitional point in a continuous cycle of creation and destruction. This perspective opens the door for meaningful discussions about events that could precede our current universe, although these ideas remain speculative and challenging to verify. These explorations push the boundaries of our understanding, inviting us to consider the limits of scientific inquiry. The quest to make sense of the time before the Big Bang underscores humanity's deep-seated desire to comprehend not only the origins of the universe, but also the fundamental nature of reality itself. It poses profound philosophical questions about existence, the flow of time, and what before could even mean in a context where time itself did not exist. As we approach the Big Bang singularity, our conventional understanding of time begins to break down in remarkable and challenging ways. At this singularity, equations of physics, particularly those outlined in general relativity, reach a point where the curvature of space-time becomes infinitely steep. This suggests a situation where the laws that govern the fabric of the universe cease to function as we expect, rendering our traditional notion of time effectively meaningless. Near the Big Bang, the density and temperature of the universe were extraordinarily high, creating extreme conditions. In this environment, time as we know it, a linear progression of past, present, and future, is no longer a reliable measure. Instead, all events seem to converge into a point where our usual chronological framework collapses. Thus, trying to apply the standard rules of time leads us into a realm of paradox and confusion, where notions such as before and after lack clear definitions. This breakdown of time highlights the limitations of our current scientific understanding. While quantum mechanics offers insights into the behavior of particles at incredibly small scales, it has not yet been reconciled with the expansive framework of general relativity. Approaches such as quantum gravity aim to bridge this gap, offering potential pathways to understand how time and space might behave at the singularity. However, these theories remain in the realm of theoretical physics and continue to provoke further questions. The implications of this breakdown challenge our very conception of reality, compelling us to reconsider fundamental aspects of existence. They encourage thinkers and scientists alike to venture beyond traditional boundaries, exploring not just what came before the Big Bang, but what it truly means to experience time and space in a universe marked by such extraordinary beginnings. The pursuit of understanding time's role in the cosmos ultimately enriches our appreciation for the intricate nature of reality itself, drawing us into the depths of the mysteries that lie beyond our current knowledge. Imaginary time is a compelling concept introduced by the theoretical physicist Stephen Hawking to help make sense of certain cosmological phenomena, especially regarding the early universe. In simple terms, imaginary time is a mathematical construct that arises when time is treated as a complex number rather than a real number. In this context, while we normally perceive time as flowing from the past into the future, imaginary time allows us to visualize time as a dimension that behaves more like space, where the standard distinctions between past and future may become blurred. In Hawking's model of the early universe, the use of imaginary time helps to address the singularity associated with the Big Bang. The transition from real time to imaginary time effectively smooths out the infinite densities and temperatures that arise at the singularity. By employing this approach, the notion of an initial boundary or starting point of the universe can be reimagined as a rounded-off surface rather than a drastic edge. This leads to the idea of a universe that is self-contained, without a beginning or end, and eliminates the need for a traditional starting moment. Imaginary time plays a crucial role in cosmological models that describe the universe's evolution in a way that is consistent with quantum mechanics. In Hawking's view, when one applies imaginary time, it becomes easier to visualize the early universe as a kind of four-dimensional sphere known as a no-boundary condition. This framework allows scientists to explore scenarios where the universe does not have a singular point of creation, but rather a seamless fabric of space and time that was expanding from a state of high energy and density. Exploring the concept of imaginary time invites us to rethink our assumptions about the very nature of the universe and its origins. It challenges the traditional linear perspective of time, encouraging us to consider a more complex and nuanced understanding of how the universe might have arisen, its initial conditions, and the fabric of reality itself. This theoretical exploration serves not only to illuminate the mysteries of the cosmos, but also to enhance our comprehension of time's fundamental role in shaping the universe we observe today. Different pre-Big Bang theories tackle the concept of time in varied and intriguing ways, each providing unique perspectives on what might have existed before the beginning of our observable universe. One prominent model is the Cyclic universe theory, which proposes that the universe undergoes endless cycles of expansion and contraction. In this framework, time is not linear but rather operates in a loop, with each cycle bringing about a new Big Bang followed by a period of expansion. This approach implies that time has no ultimate origin, but is rather an ongoing process shaped by the universe's repetitive nature. Another theory that addresses the concept of time is the ekpyrotic scenario, which suggests that our universe arose from the collision of two three-dimensional branes within a higher dimensional space. In this model, time may have existed in some form prior to the Big Bang, emerging as the physical conditions changed drastically due to the interaction of these branes. Here, time behaves like a dynamic variable that can evolve with the interactions of the universe's fundamental structures, offering a perspective where time has a different history and shape than that of our conventional understanding. Quantum gravity theories also present compelling insights into time before the Big Bang. These theories explore how time and space might behave in contexts where quantum effects cannot be ignored, typically at very high energies. In this framework, time may lose its familiar structure, behaving less like a linear progression and more like an emergent phenomenon that arises from more fundamental aspects of the universe. Some proposals within these theories suggest that at the Planck scale, the very concept of time could dissolve into a network of interrelated quantum events, where temporal distinctions lose meaning. Finally, the concept of timelessness emerges in speculative discussions about the state before the Big Bang. Some physicists argue that if the universe originated from a quantum state, then traditional time may not have existed. The early universe might be described by a timeless realm where space and events existed in a superposition of possibilities, suggesting a complex relationship between time and existence that challenges our basic intuitions. Each of these theories showcases the diverse and rich approaches to understanding time in pre-Big Bang conditions, pushing the boundaries of our knowledge and inviting further exploration into the true fabric of reality. The arrow of time is a term that refers to the one-way direction in which time appears to flow. There are several arrows of time that describe different aspects of this phenomenon. The most prominent is the thermodynamic arrow, which is based on the second law of thermodynamics. This law states that in an isolated system, entropy or disorder tends to increase over time. As a result, we observe physical processes flowing from states of lower entropy to those of higher entropy, effectively giving time its apparent direction. Another important arrow of time is the psychological arrow, which relates to our experience of time as humans. This reflects how we remember the past but not the future, as our consciousness is anchored in the flow of experiences. There is also the cosmological arrow, which aligns with the expansion of the universe, indicating that time moves forward in coherence with the growth and evolution of cosmic structures. When we consider the behavior of the arrow of time before the Big Bang, things become particularly complex and intriguing. If we accept that time as we understand it began at the moment of the Big Bang, the question arises, what does it mean to speak of time before this event? Some theories suggest that the arrow of time may not have existed in a conventional sense prior to the Big Bang. Conditions in a pre-Big Bang scenario could have been so fundamentally different that our current notions of temporal progression and causality would not apply. In certain speculative models, such as the cyclic universe theory, the arrow of time could have flipped with each cycle, leading to different orientations of time in each iteration. This presents a fascinating context in which time may behave in ways that are not only unfamiliar to our everyday experience, but also challenge the very nature of time itself. If time in some form did exist before the Big Bang, it could have been characterized by a low entropy state, which would transition into the higher entropy state we observe today, thus establishing the directionality of the arrow of time. Ultimately, the concept of the arrow of time invites profound questions about reality and existence. As we probe the mysteries of the universe's origins, understanding how time functioned in those early moments or even before helps deepen our insight into the mechanisms that govern both the cosmos and our place within it. Through exploring these intricate relationships, we gain a richer perspective on the fundamental nature of time itself. Entropy plays a crucial role in our understanding of time and its directionality, particularly in the context of the universe's origins. As mentioned earlier, the second law of thermodynamics states that in an isolated system, entropy tends to increase over time. This principle suggests a natural progression from order to disorder, meaning that systems evolve towards states of higher entropy. Consequently, our perception of time is strongly linked to this increase in entropy, as we associate the flow of time with the movement from organized lower entropy states to those that are more chaotic and disordered. When we attempt to apply these ideas to the concept of time before the universe, it leads to some intriguing questions. If we consider the Big Bang as the origin of the universe, it is generally understood to represent a state of extremely low entropy. This means that prior to the Big Bang, the universe must have existed in a condition even less entropic, which is counterintuitive to our typical understanding of cosmic evolution. Speculations about this pre-Big Bang condition often involve discussions of a high-energy vacuum state or a similar scenario where entropy is minimal. The idea that entropy could have been even lower than at the moment of the Big Bang provides a basis for exploring what happens to the arrow of time. If time began with the Big Bang, the increase in entropy would mark our forward movement through time, highlighting a shift from a highly ordered state to more disordered configurations of matter and energy. This raises the question of whether, in a pre-Big Bang universe, time itself existed in a meaningful way. If entropy was at such low levels, it's possible that the conventional arrow of time, which relies on disorder's progression, may not have been relevant in the same sense. Additionally, exploring entropy in the context of pre-Big Bang theories informs discussions about cyclical models or multiverse theories. In cyclic models, each cycle of the universe could reset entropy in some way, providing a framework where the concept of time and entropy is continually redefined. Through these explorations, we grapple with the complex relationship between entropy, time, and the universe's very origins, shedding light on the intricate nature of reality itself. Understanding how entropy connects to these primordial conditions invites profound reflections on the nature of existence and the underlying structures that shape the cosmos. Quantum mechanics offers intriguing insights that could enhance our understanding of the nature of time at the Big Bang, bridging gaps in our knowledge and highlighting the complexities of the universe's origins. At its core, quantum mechanics reveals that at extremely small scales, particles and phenomena behave in ways that defy our classical intuitions. This framework encourages scientists to rethink how time might have operated in the incredibly dense and energetic conditions surrounding the Big Bang. One significant area where quantum mechanics intersects with cosmology is through the concept of quantum fluctuations. These fluctuations could have played a pivotal role in the early universe, where the vast high-energy state was characterized by uncertainty and probabilistic events. In this context, time may not have followed a linear trajectory as we understand it, but could instead have manifested in a more fluid manner, where different quantum possibilities coexisted. This notion challenges the conventional linear narrative of time, suggesting that time itself might be emergent, shaped by quantum interactions, rather than bound to a straightforward progression. Further exploration within the framework of quantum gravity aims to unite the principles of general relativity and quantum mechanics. Theories such as string theory propose that at the Planck scale, space and time could become quantized, meaning they might inherently possess a granular structure rather than being continuous. If true, this could have profound implications for how we understand the initial moments of the universe and the nature of time itself during the Big Bang. The idea of a quantum realm infusing the very fabric of space-time could suggest that time, in its conventional sense, loses meaning in the vicinity of the singularity. Additionally, considering time in the context of entanglement and non-locality, key aspects of quantum mechanics, opens further pathways for exploring the early universe. As entangled particles can exhibit correlations regardless of distance, it raises questions about how events may have been connected in the primordial cosmos. This could suggest a more intricate and interconnected nature of temporal progression that might fundamentally differ from our everyday experiences. Quantum mechanics invites us to re-examine the nature of time at the Big Bang, potentially redefining our understanding of its flow and characteristics. By incorporating quantum principles into cosmological models, scientists can strive to unravel the mysteries surrounding the universe's origins, pushing the boundaries of what we know about both time and existence itself. Through this exploration, we may discover deeper insights into the fundamental mechanisms that shape reality and the intricate relationship between time and the cosmos. The problem of time in quantum gravity addresses a profound and complex issue arising from the interplay between general relativity and quantum mechanics. As physicists seek to create a unified theory that can describe both the large-scale structure of the universe and the behavior of particles at the quantum level, they encounter significant challenges regarding how time behaves in these different frameworks. In general relativity, time is treated as a dimension similar to space, woven into the fabric of space-time, while quantum mechanics operates under principles that do not incorporate time in the same straightforward manner. One of the key aspects of the problem of time is that, in quantum mechanics, the fundamental equations describing quantum systems do not explicitly include time as a variable in the same way that classical physics does. Instead, the evolution of quantum states is often described by a wave function, which captures probabilities regarding different outcomes, but does not necessitate a classical notion of time passing. This raises challenges when attempting to merge these approaches, particularly in understanding how time operates at the very early moments of the universe, such as those associated with the Big Bang. This problem becomes particularly acute when considering the early universe, where conditions were governed by extreme gravitational effects, making a unified description of space-time and particles essential. In this context, one might ask, how do we conceptualize time near the singularity? As conventional models suggest that time and space originated at the moment of the Big Bang, the question of what happens to time before or within such a singularity, or how temporal progression aligns with quantum states, remains a topic of intense debate. Various approaches have been proposed to tackle the problem of time in quantum gravity. One idea posits that instead of treating time as a standalone dimension, it could emerge from more fundamental elements of reality, potentially intertwined with quantum entanglements and relationships between particles. Thus, time could be seen as an effective parameter resulting from the dynamics of quantum states rather than an independent backdrop against which events unfold. This exploration of the problem of time not only advances theoretical frameworks, but also sparks deeper inquiries about the nature of reality itself. By grappling with these issues, scientists hope to gain insights not just into the workings of the early universe, but also into the fundamental structures that underpin spacetime. Understanding how time relates to quantum mechanics ultimately holds the potential to reshape our comprehension of the cosmos and our very existence within it, shedding light on the intricate tapestry of reality. The concept of causality, which describes the relationship between causes and their effects, faces significant challenges when considered in the context of conditions before the Big Bang. Traditionally, we understand causality as a fundamental aspect of time, where events delineate a clear chain of cause and effect. However, the Big Bang marks a point where the conventional notions of time and space began, leading to intriguing questions about how causal relationships might have operated, or if they even existed, prior to this moment. In some pre-Big Bang theories, such as the Cyclic universe model, the universe undergoes infinite cycles of expansion and contraction. In this framework, causality can be thought of as an ongoing process, where each cycle may impact subsequent ones. While this setup provides a sort of continuity, it still raises questions about what before means in a context where time itself is inherently cyclical. If each universe follows the previous one, the relationship between cause and effect could undergo transformations with each cycle, complicating our conventional understanding. Some quantum gravity models suggest that in the very early universe, or perhaps prior to it, the traditional notion of causality may not apply at all. At extremely small scales, particularly near what is called the Planck scale, the interplay of quantum mechanics and gravity leads to a reality that differs significantly from our everyday experience. In a realm where quantum fluctuations dominate, events may occur without clear causal relationships, as particles may be entangled or exist in superpositions of states. This raises intriguing possibilities about the interconnectedness of events, where influences can transcend classical causal links. Furthermore, if we explore the concept of a timeless state, as suggested by certain theoretical physicists, we find an even more profound departure from established causality. In such scenarios, where neither time nor space are defined in the conventional sense, the very idea of cause and effect may dissolve. Rather than a linear sequence of events, there may exist a collection of potentialities, governed by principles of quantum mechanics, where outcomes are determined by probabilities rather than direct causation. The notion of causality before the Big Bang challenges our traditional understanding of how events are linked in time and space. It encourages scientists and philosophers alike to explore complex models that either redefine or dissolve conventional causal frameworks. As we investigate these profound questions, we deepen our comprehension of the universe's origins and the fundamental nature of reality itself, leading to richer insights into the intricate web of relationships that may shape the cosmos. The second law of thermodynamics is fundamental to our understanding of the universe and plays a significant role in discussions surrounding pre-Big Bang time. This law states that in an isolated system, the total entropy, or measure of disorder, tends to increase over time. This principle is essential in establishing our directionality of time, as it highlights a natural progression from ordered states to disordered ones. When considering the conditions of the universe, the second law helps frame discussions about what may have transpired prior to the Big Bang and what implications that might have for our understanding of time itself. In the context of the Big Bang, it is generally accepted that the universe began in a state of extremely low entropy. This low entropy condition would mean that the universe, as it expanded and evolved, moved towards higher entropy, a critical aspect of its developmental trajectory. Understanding the implications of this transition emphasizes that time, as we perceive it, is closely linked to this increase in entropy. As we explore pre-Big Bang conditions, we encounter crucial questions related to the state and behavior of entropy before the universe as we know it came into existence. Looking at pre-Big Bang scenarios, one possible interpretation is that the universe existed in an even lower entropy state before the Big Bang. This poses an intriguing question. How can we conceptualize a state of existence where entropy is minimal or zero? Discussions around this idea often lead to speculation about high-energy vacuum states or fluctuations in a quantum field that existed prior to the singularity. These pre-Big Bang models propose that while entropy increased rapidly after the Big Bang, the conditions that inspired the creation of our universe might have been radically different, necessitating a re-evaluation of how we understand time in that context. The second law of thermodynamics also contributes insight into more complex models, such as those describing cyclic or oscillating universes. In these models, the universe experiences repeated expansions and contractions, suggesting a cyclical nature of entropy. In this framework, each cycle could reset entropy to lower levels, allowing time to be viewed as a loop rather than a straight line. Such perspectives help to expand our understanding of pre-Big Bang time, indicating that the relationship between entropy and time could be more nuanced than our traditional linear interpretation. Ultimately, the second law of thermodynamics serves as a vital cornerstone in contemplating pre-Big Bang time and conditions. It highlights the importance of entropy in shaping time's direction, while challenging us to explore deeper questions about the nature of existence, reality, and the fundamental mechanisms that govern the universe. Through this exploration, we gain richer insights into how the universe evolved from its primordial state and how our understanding of time itself might be redefined. The quantum foam hypothesis refers to a concept in quantum gravity that visualizes space-time as being composed of very small, fluctuating structures at the Planck scale, which is approximately 10 to the negative 35th meters. Proposed by physicist John Wheeler in the mid-20th century, this idea suggests that beneath the smooth fabric of space-time as we perceive it, there exists a tumultuous, dynamic state characterized by constant fluctuations and activity. This foam-like quality of spacetime implies that at incredibly tiny scales, spacetime behaves in a fundamentally different manner, with particles and fields not settling into a stable geometry, but rather undergoing rapid and unpredictable changes. In relation to pre-universe conditions, the quantum foam hypothesis provides a compelling framework for thinking about the state of the universe prior to the Big Bang. The notion of a foamy spacetime aligns well with certain interpretations of quantum mechanics, where uncertainty and indeterminacy dominate. In this context, the early universe might not have been a singular event, but instead a swirling mass of quantum fluctuations, where particles appeared and disappeared, and regions of spacetime constantly interacted in highly unpredictable ways. This model creates an intriguing perspective on what could have existed before the conventional understanding of the universe took form. Instead of a static vacuum or a singular point, the idea of quantum foam suggests a vibrant, energetic landscape populated by fluctuations that could give rise to various physical phenomena. Some theorists propose that these quantum fluctuations might have been responsible for instigating the Big Bang itself, effectively acting as the seeds from which our universe emerged. In this light, the quantum foam serves as both a precursor to the universe and a mechanism through which the initial conditions necessary for the Big Bang could have developed. The implications of the quantum foam hypothesis extend beyond cosmology, challenging our understanding of spacetime and reality itself. If spacetime is indeed foamy at its fundamental level, then it invites questions about the very nature of time. For instance, if spacetime is constantly in flux, what does that imply for causality and the flow of time? Furthermore, this perspective could lead to a greater understanding of how quantum mechanics and general relativity might come together, providing insights that could lead to a more unified theory of physics. The quantum foam hypothesis offers a captivating lens through which to explore pre-universe conditions. It encourages consideration of a dynamic, fluctuating state of reality that foreshadows the emergence of the universe and challenges traditional notions of spacetime, time, and causality. By investigating these concepts, we deepen our understanding of not only the origins of the universe, but also the fundamental characteristics of existence itself. The concept of dimensionality is pivotal when exploring the state before the Big Bang, as it invites us to reconsider the very nature of space and time in a context that traditional physics may not adequately describe. In our everyday experience, we perceive the universe as having three spatial dimensions and one temporal dimension, which combine to form what we recognize as the four-dimensional spacetime of Einstein's theory of relativity. However, theories that attempt to grapple with conditions before the Big Bang often suggest that our conventional understanding of these dimensions might not apply in a simplistic manner. In various pre-Big Bang theories, the dimensional structure of the universe may be significantly different from what we experience today. For instance, string theory postulates that additional spatial dimensions beyond the familiar three may exist, potentially up to 10 or even 11 dimensions. These extra dimensions may be compactified or hidden in such a way that they are not observable at macroscopic scales. In this framework, the early universe could be visualized as existing in a higher dimensional space, where time, as we understand it, may not even have been a relevant factor. Instead, space and time might have been part of a unified multidimensional construct, with more degrees of freedom than we can currently conceive. Moreover, the idea of a timeless state prior to the Big Bang gives rise to further considerations regarding dimensionality. Some theoretical models propose that before the initiation of our universe, space-time itself may not have been established in the way we typically understand it. Instead, it could have existed in an undifferentiated state, where dimensions as we know them were not defined. In such a scenario, the familiar notions of distance and time as relational properties would give way to a more abstract and fundamental reality. This reconceptualization of dimensionality challenges traditional causal relationships. If higher dimensions were at play, the interactions and events that we associate with three-dimensional space and linear time would have been governed by entirely different rules. Such insights could illuminate how the universe transitioned from this primordial state into the structured four-dimensional cosmos we observe today. The concept of dimensionality before the Big Bang invites us to explore complex ideas about the nature of reality and the foundational structures of the universe. It encourages scientists and philosophers alike to question what dimensions mean in a cosmic context, particularly regarding the origins of space and time and the mechanisms that shaped the universe. By examining these ideas, we enhance our understanding of the interplay between dimensionality, causality, and the fundamental nature of existence itself. Supersymmetry is a theoretical framework in particle physics that suggests a profound relationship between bosons, the force-carrying particles, and fermions, the matter particles. The idea posits that for every known particle, there exists a corresponding superpartner with different spin characteristics. Although supersymmetry has yet to be experimentally confirmed, it provides intriguing possibilities for our understanding of the fabric of pre-universe existence, particularly in how it relates to issues like unification, stability of particles, and the fundamental structure of reality itself. One of the significant implications of supersymmetry is its potential to address problems associated with high-energy physics and the behavior of quantum fields. If supersymmetry holds true, it could help stabilize the mass of particles, thereby alleviating concerns about quantum fluctuations that might arise at extreme energies, such as those present in the early universe or at the moment of the Big Bang. In this sense, supersymmetry could contribute to a more coherent understanding of the conditions present before our universe emerged, providing a well-defined structure for the types of particles and interactions that existed during this primordial phase. Furthermore, supersymmetry plays a critical role in various models of cosmology that seek to explain the evolution of the universe. For example, the concept of supersymmetric inflation suggests that the rapid expansion of the universe in its early moments might be fueled by scalar fields associated with supersymmetric particles. This approach offers a framework to understand how the universe transitioned from a highly energetic state to the observed expansion, potentially providing mechanisms that lead to low entropy conditions necessary for the Big Bang. It helps create a more picture-perfect scenario in which the pre-universal state could smoothly evolve into the expanding cosmos we inhabit today. Another profound aspect to consider is how supersymmetry could connect to higher dimensional theories, such as string theory. In these frameworks, space-time could include additional dimensions where supersymmetry operates, shaping the fundamental physical laws we observe. In a pre-universe context, such models could suggest that the characteristics of these extra dimensions, influenced by supersymmetry, play a vital role in the formation of our universe, influencing the types of interactions and particles that became manifest after the Big Bang. Ultimately, the role of supersymmetry in the fabric of pre-universe existence introduces a rich tapestry of possibilities that extend our understanding of the cosmos. By potentially unifying the particles and fundamental forces of nature, supersymmetry provides avenues to explore the deep connections that weave the fabric of reality. Through this exploration, scientists hope not only to uncover the nature of our universe's origins, but also to grasp the underlying principles that govern existence itself. Theories of quantum gravity offer intriguing perspectives on the nature of space before the Big Bang, proposing that space may not function in the same manner we typically understand. These theories aim to merge the principles of quantum mechanics, which govern the behavior of particles at the smallest scales, with general relativity, which describes gravity and the large-scale structure of the universe. As scientists explore this intersection, they begin to uncover how space might have behaved in a primordial state. One prominent approach within quantum gravity is loop quantum gravity, which suggests that space is quantized, composed of discrete chunks or loops, rather than being continuous. In this framework, the fabric of space can be visualized as being made up of tiny, indivisible units, leading to a restructuring of how we conceptualize space-time at its most fundamental level. This implies that prior to the Big Bang, space could have existed in a highly non-classical form, characterized by unpredictable fluctuations and connections that defy conventional descriptions. Additionally, theories like string theory propose that our familiar three-dimensional space might be embedded in a higher dimensional framework, where additional dimensions exist but are compactified and inaccessible at low energies. Before the Big Bang, these extra dimensions might have played a crucial role in shaping the dynamics of space and time. In such models, the interactions of branes and strings in these higher dimensional spaces could have contributed to the transformations that led to our current universe. The concept of a timeless or pre-space-time state emerges in some theoretical frameworks, where traditional notions of space and time might not have applied before the Big Bang. In these scenarios, reality could be represented by fundamental quantum states that do not necessarily possess spatial or temporal characteristics. Instead of a structured expanse, pre-Big Bang conditions might resemble a quantum vacuum filled with possibilities rather than established structures. This idea challenges the very foundations of how we perceive space and could lead to an understanding of a more interconnected and dynamic nature of reality. Furthermore, approaches that utilize the notion of quantum foam propose that space may exist as a fluctuating medium full of transient structures, shaping interactions and events at extremely small scales. This helps illustrate how, even in a primordial state, the internal characteristics of space could evolve dramatically, ultimately leading to the conditions that facilitated the Big Bang and the universe's subsequent expansion. Theories of quantum gravity provide a rich and varied tapestry of ideas regarding the nature of space before the Big Bang. These frameworks invite us to rethink our notions of space, time, and reality itself, suggesting that the characteristics of existence at the universe's origins may not conform to our current understandings. By delving into these concepts, scientists aim to uncover deeper insights into the fabric of the cosmos and the fundamental mechanisms that govern its evolution. The holographic principle is a fascinating concept, suggesting that all the information contained within a volume of space can be represented as a theory residing on the boundary of that space. This means that three-dimensional objects could actually be understood as projections from two-dimensional information on a surface. The idea emerged from studying black holes, where it was found that the entropy, or information content, of a black hole is proportional to the area of its event horizon rather than its volume. The implications of the holographic principle extend into the realm of the universe's origins, especially when considering the state before the Big Bang. If the universe can be visualized as a hologram, it raises the question of whether the actual pre-universe state could exist on a similar boundary. This could mean that information and physical laws, which seemingly govern our three-dimensional space, are encoded on a distant surface, perhaps hinting at conditions or laws that existed before the universe as we know it came into being. In this context, the pre-universe state might be seen not as a tangible collection of matter or energy, but rather as a condensation of information awaiting an expansion into the complex universe we experience today. The idea leads to exciting possibilities about what form that information might take and how it could be accessed or understood if our current models of physics are extended to incorporate this principle. Ultimately, the holographic principle challenges our understanding of space and reality. It invites researchers to explore how the boundaries of our universe might hold secrets about its creation and structure, perhaps suggesting that the cosmos operates on deeper, more fundamental principles than currently understood. This exploration pushes the limits of cosmology and theoretical physics as scientists continue to unravel the mysteries of the universe's inception. The concept of information plays a crucial role in our understanding of the fabric of pre-universe existence, particularly when we examine how information might have existed before matter and energy came into being. In modern physics, information is often seen as a fundamental building block of reality, potentially entwined with the very fabric of space-time. The idea that information could be foundational suggests that the pre-universe state might not have been void of structure, but rather rich in encoded possibilities that would eventually lead to the universe we know. If we apply the holographic principle, as mentioned earlier, it posits that the universe emerges from information residing on a boundary. This could imply that before the onset of the Big Bang, the essential characteristics of our universe, such as physical laws and fundamental constants, were all represented in some abstract form. Thus, these pre-existing informational attributes could have played a critical role in governing how the universe unfolded once space and time began to emerge. Moreover, the relationship between information and reality challenges traditional notions of existence. Rather than perceiving the universe as built exclusively from physical matter, we may view it as a manifestation of underlying information. In a way, this perspective mirrors how information technology operates today. Just as data becomes tangible through various means, such as computers or digital media, the universe could emerge from pre-existing informational constructs that became real during the Big Bang. Understanding the pre-universe existence purely through the lens of information offers a transformative approach to cosmology. If the universe arose from a tapestry of information, questions about its initial conditions, structure, and evolution take on new significance. This framework encourages exploration into what the universe truly is at its core and how information shapes our reality, possibly propelling us toward groundbreaking discoveries about the nature and origin of everything we observe. Quantum entanglement could play a significant role in our understanding of the pre-Big Bang state by implying a form of connectivity between particles that transcends the traditional framework of space-time. Quantum entanglement occurs when particles become interconnected in such a way that the state of one particle can instantaneously affect the state of another, regardless of the distance separating them. This peculiar phenomenon hints at a deeper layer of reality, where local interactions may not fully define the relationships between fundamental components of the universe. The notion of entanglement is particularly interesting when considering the conditions leading up to the Big Bang. If we imagine a pre-Big Bang state filled with a quantum fabric, entangled particles could represent a vast web of interdependence, with each particle influencing the behaviors of others. This interconnectedness might suggest that the cosmos had a unified state before it expanded into the distinct regions of space and time we observe today, hinting at a form of coherence that governed the behavior of energy and matter before the universe gained its current structure. Furthermore, entanglement raises intriguing questions about the nature of information in a pre-universal context. It is conceivable that the information contained in entangled states could encode the properties of the universe that would emerge after the Big Bang. This aligns with theories suggesting that the universe might have originated from a highly entangled quantum state that subsequently underwent a phase transition to realize the classical dimensions we experience now. Exploring the role of quantum entanglement in the pre-Big Bang state could provide new avenues for understanding how the cosmos transitioned from a highly correlated energy-dense state to the expanding universe characterized by a variety of distinct regions. As scientists delve deeper into the intertwining relationships between quantum mechanics and cosmology, the nature of entanglement may reveal essential insights into not only the origins of the universe, but also the fundamental workings that govern its ongoing evolution. Different theories offer various perspectives on how fundamental forces might have interacted or existed prior to the universe's expansion. The four known fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, described by our current understanding, could have behaved quite differently in the extreme conditions present before the Big Bang. In many theories, these forces may have been unified, operating under a single framework rather than as distinct interactions as we perceive them today. One prominent theory is the grand unified theory, which suggests that at very high energies, the three non-gravitational forces, strong, weak, and electromagnetic, could merge into a single force. This unification would imply that before the universe began its expansion, these forces were not separate entities but part of a more fundamental interaction. Research into high-energy particle collisions provides insights into how these forces may have behaved under conditions similar to those believed to be present during the universe's early expansion. In addition, theories like string theory propose that the fundamental forces originate from tiny vibrating strings rather than point particles. In this framework, the behaviors of forces and particles arise from the different vibrational modes of these strings. Before the expansion of the universe, when these strings were compacted into a highly dense state, the characteristics of the forces could have been markedly different, possibly merging into a single force that governs the interactions in that primordial state. Theories exploring quantum gravity also suggest that the fabric of space-time itself may have undergone radical transformations near the singularity of the Big Bang. In such scenarios, gravity might have acted very differently, with quantum effects playing a dominant role at extremely small scales. These quantum gravitational effects could provide a deeper understanding of how forces interacted before the expansion and offer crucial insights into the very early universe's dynamics. By examining these various theoretical frameworks, researchers aim to piece together a more complete picture of how fundamental forces emerged from an interconnected state. Each theory contributes to our understanding of the universe's origins, illustrating how gravitation and other interactions may have transformed as the cosmos transitioned from a singularity to the large-scale structure we observe today. Symmetry plays a pivotal role in understanding the state before the Big Bang, enriching our grasp of fundamental forces and particles in the early universe. In physics, symmetry refers to a property that remains invariant under specific transformations, and it can manifest in various forms, including spatial, temporal, and internal symmetries. These symmetries form the backbone of our physical theories and are especially significant in the context of high-energy states, such as those thought to exist just before the universe's expansion. In many theoretical frameworks, such as grand unified theories, symmetry implies that the fundamental forces were unified in a symmetric state prior to the Big Bang. At such extreme conditions, the strong, weak, and electromagnetic forces were indistinguishable, governed by a single force that later broke into distinct interactions as the universe cooled and expanded. This concept of symmetry breaking is vital, as it suggests that the diverse forces and particles we observe today arose from a more fundamental, uniform state. The mechanisms behind this symmetry breaking are crucial in shaping the cosmos and its development. Moreover, the role of symmetry extends into the realm of quantum field theory, where particle properties emerge through symmetry principles. The search for symmetries explains how particles get their masses via mechanisms such as the Higgs field, which itself is linked to symmetry breaking. Applying this to the pre-Big Bang state, one can hypothesize that invariant conditions contributed to the characteristics and laws that govern our universe. Considering the implications of symmetry can also illuminate the conditions leading to the Big Bang singularity. Certain theories propose that the universe began from a highly symmetric state, where fluctuations could give rise to the asymmetries necessary for the development of the rich structures we see today, from galaxies to stars. Understanding the role of symmetry in this context offers valuable insights into the universe's early conditions and could pave the way for discovering new physics beyond our current models. The concept of matter and antimatter is central to our understanding of the universe, and examining its implications for pre-universe conditions opens up fascinating avenues of exploration. In our current universe, matter and antimatter are produced in equal amounts through various processes, but they behave in opposite ways. When they encounter each other, they annihilate, releasing energy. This raises profound questions about the conditions present before the Big Bang, especially since we observe a universe predominantly made of matter, with only trace amounts of antimatter. Theories about the early universe suggest that it likely began with equal amounts of matter and antimatter. In a highly dense, hot state immediately following the Big Bang, particle-antiparticle pairs would have been continuously created and annihilated. However, something must have disrupted this balance, leading to the observed asymmetry in favor of matter. Various mechanisms have been proposed to account for this imbalance, such as the effects of CP violation, where the laws of physics might differ slightly for matter and antimatter. This violation could have allowed slight preferential production of matter over antimatter during the universe's evolution. Delving into pre-universal conditions also surfaces intriguing questions regarding the nature of vacuum fluctuations and quantum fields. In certain models, it is theorized that the vacuum could have supported temporary manifestations of particle-antiparticle pairs. These fluctuations might have influenced the dynamics of the early universe and played a role in generating the conditions necessary for the eventual predominance of matter. Furthermore, the interactions involving matter and antimatter may illuminate our understanding of cosmic inflation, a rapid expansion phase thought to occur shortly after the Big Bang. If different regions of space encountered varying amounts of matter and antimatter, this could lead to localized regions of annihilation, contributing additional complexity to the evolution of the universe. Exploring the relationship between matter and antimatter in the context of pre-universe conditions provides vital clues about the processes that shaped the cosmos. As researchers continue to investigate these fundamental concepts, they inch closer to understanding not only why our universe is matter-dominated, but also the fundamental laws that governed its origins. Observational evidence related to the pre-Big Bang theories is both intriguing and complex, as it touches upon the very nature of the universe's origins. While we cannot directly observe conditions before the Big Bang due to the limitations imposed by the event itself, various indirect observations and theoretical models provide compelling support or challenge for ideas regarding the universe's early state. One of the most significant pieces of evidence comes from the cosmic microwave background radiation. This relic radiation, which fills the universe and represents the afterglow of the Big Bang, supports the idea of a hot, dense state before space and time expanded. Measurements of the cosmic microwave background's temperature fluctuations reveal a wealth of information about the early universe, including its density, composition, and the distribution of matter. Some pre-Big Bang theories, such as inflationary models, emphasize rapid expansion, and observational data aligns well with these ideas, reinforcing their plausibility. Another critical piece of evidence comes from the large-scale structure of the universe. The distribution of galaxies and galaxy clusters provides insights into how matter evolved since the Big Bang. The observations of the universe's expansion rate, especially through redshift measurements of distant galaxies, indicate that the universe is expanding. This insight supports the notion that the universe has been evolving from a very different state. Some pre-Big Bang models theoretically predict specific patterns in structure formation that can be compared with observed large-scale structures. However, not all observations align neatly with specific pre-Big Bang theories. Some challenges arise from the entropy of the universe. The second law of thermodynamics suggests that the universe tends toward increased entropy over time. The idea that the universe originated from a highly ordered state before the Big Bang raises questions about how this high entropy fit with observed low entropy conditions. Models that propose oscillating universes or cyclic models may attempt to address this by suggesting that the universe undergoes repeated phases of expansion and contraction, which offers an alternative to a singular beginning. While observational evidence from cosmic microwave background radiation and the structure of the universe supports specific pre-Big Bang theories, there remain unanswered questions and challenges, particularly concerning entropy. The ongoing exploration and refinement of these observational insights will continue to shape our understanding of the enigmatic conditions that preceded the Big Bang. Cosmic microwave background radiation is a vital piece of evidence that informs our understanding of the early universe. This remarkable phenomenon represents the afterglow from the hot, dense state that existed shortly after the Big Bang, approximately 380,000 years later, when the universe cooled enough for protons and electrons to combine and form neutral hydrogen atoms. This process allowed photons to travel freely, marking the moment when the universe became transparent to radiation. The cosmic microwave background serves several key purposes in cosmology. Its uniformity across the sky indicates that the early universe was extraordinarily homogeneous and isotropic when it cooled down and transitioned from the hot plasma state. However, slight fluctuations in temperature are also present, revealing tiny variations in density that would later evolve into the structures we observe today, such as galaxies and galaxy clusters. By studying these temperature fluctuations, scientists can glean insights into the initial conditions that led to the universe's large-scale structure. Moreover, the cosmic microwave background provides crucial information about fundamental cosmological parameters, such as the density and composition of the universe. By analyzing its spectrum, researchers can estimate the amounts of ordinary matter, and dark energy that make up the universe today. These measurements have led to significant progress in understanding how these components interact and influence the universe's evolution. In addition, the cosmic microwave background radiation has strong implications for theoretical models, such as inflationary theory. This theory posits that a rapid expansion of the universe happened very early in its history, smoothing out initial irregularities. The observed fluctuations in the cosmic microwave background corroborate predictions made by inflationary models, supporting the idea that such an event played a crucial role in shaping the early universe's properties. The cosmic microwave background radiation is thus a cornerstone of modern cosmology, offering a direct link to the conditions that existed shortly after the Big Bang. By continuing to study this relic radiation, scientists deepen their understanding of the universe's origins, development, and the fundamental forces that shaped it. Gravitational waves represent a groundbreaking avenue through which scientists can explore the mysteries of the universe, including potential states before the Big Bang. Produced by some of the most violent and energetic processes in the cosmos, such as colliding black holes or neutron stars, these ripples in space-time carry information about their origins that is often unobscured by other factors that interfere with light, such as dust and gas. One of the most tantalizing aspects of gravitational waves is their potential to encode information about the very early universe, particularly during epochs like cosmic inflation. During inflation, a rapid exponential expansion of the universe is thought to have occurred within a fraction of a second following the Big Bang. If gravitational waves were produced in this era, their distinctive patterns could reveal insights into the energy scale of inflation, the dynamics of the early universe, and the fundamental physical conditions present prior to the Big Bang. Current and future gravitational wave observatories like LIGO and the upcoming space-based observatory LISA aim to detect these primordial waves. Detection would not only provide valuable confirmation of inflationary models, but could also indicate characteristics of the fundamental forces governing the universe's evolution during that time. For instance, gravitational waves could provide evidence of the potential energy landscape driving inflation and could even hint at specific symmetries in physical laws that may have existed. Furthermore, researchers are exploring whether gravitational waves could hold clues about the transition from the quantum realm to classical behavior in the very early universe. How the universe emerged from this quantum state and how space-time itself transformed could also be accessible through gravitational waves, helping to bridge the gap between quantum mechanics and general relativity. Gravitational waves have the potential to offer profound insights into the conditions that prevailed before the Big Bang. By studying these ripples in space-time, scientists might unravel fundamental questions about the universe's origin, the mechanisms that governed its rapid expansion, and the very nature of the forces that shaped our cosmos. As detection capabilities advance, gravitational waves could open new windows into the early history of the universe, extending our knowledge beyond the limits of current observations. Testing theories about conditions before the Big Bang presents unique challenges because we encounter limitations dictated by both the nature of the Big Bang itself and the realm of modern physics, which includes quantum mechanics and general relativity. However, scientists employ a variety of observational strategies, theoretical frameworks, and experimental methodologies to explore these enigmatic conditions. One approach involves studying the cosmic microwave background radiation, which captures echoes of the universe shortly after the Big Bang. By analyzing its temperature fluctuations, cosmologists can extrapolate details about the early universe's dynamics, offering indirect evidence that informs pre-Big Bang theories. These observations can help validate or refute models of cosmic inflation or other scenarios that hypothesize specific conditions preceding the Big Bang. The data generated by missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have greatly enhanced these efforts. Another method is through the detection of gravitational waves. As mentioned earlier, gravitational waves could provide critical information about events and processes that occurred during the universe's infancy and possibly shed light on the conditions leading up to the Big Bang. The identification of gravitational wave patterns due to primordial waves, if achievable, would validate specific models regarding inflation and pre-existing states. Theoretical work also plays a crucial role in testing pre-Big Bang conditions. Physicists explore frameworks such as string theory, loop quantum gravity, and the ekpyrotic model, which posit various scenarios for the universe's origin. These theoretical constructs can generate predictions that inform what might be detectable in our current universe. Comparing these predictions against observable phenomena allows scientists to evaluate the plausibility of different theories. Additionally, laboratory experiments and high-energy particle physics, using particle accelerators like the Large Hadron Collider, can probe fundamental forces and interactions that were likely significant during the universe's earliest moments. By recreating similar conditions present shortly after the Big Bang, researchers can analyze particle behavior and interactions that lend insight into the forces and elements that shaped the universe. While testing theories about pre-Big Bang conditions is inherently complex, a combination of observational astrophysics, gravitational wave research, theoretical modeling, and high-energy particle physics provides various pathways to deepen our understanding. Through ongoing research and new discoveries, scientists strive to piece together a coherent picture of the universe's origins and the conditions that prevailed before the Big Bang. Particle accelerators play a crucial role in investigating pre-Big Bang physics by allowing scientists to recreate and study extreme conditions similar to those believed to have existed in the early universe. These powerful machines accelerate charged particles to nearly the speed of light and smash them together, generating high-energy collisions that produce various particles and phenomena. By examining these interactions, researchers can glean valuable insights into the fundamental forces and particles that governed the universe shortly after the Big Bang, and potentially even in the moments preceding it. One of the key interests in pre-Big Bang physics is understanding the unification of the fundamental forces. Particle accelerators, such as the Large Hadron Collider, provide the means to probe energy levels that could shed light on how forces like electromagnetism, the strong nuclear force, and the weak nuclear force may have merged at higher energies. These experiments can test theoretical models that predict how these forces interact under conditions similar to those of the early universe, thereby offering clues about the unification processes that might have occurred before the universe cooled and expanded. Additionally, particle collisions can create conditions that mimic the high-energy environment believed to be present during cosmic inflation, a rapid expansion just after the Big Bang. By studying the resulting particles and any potential signatures of emerging forces, researchers can gather evidence to support or challenge different inflationary models. For example, they may discover hints of new particles or interactions that point towards mechanisms that could drive inflation or support the idea of symmetry breaking, where the unified forces separated as the universe expanded. Furthermore, experiments at particle accelerators can also help scientists investigate phenomena related to the early universe's state, such as the generation of dark matter and dark energy. Understanding how particles behave under extreme conditions can help formulate hypotheses about the components that contributed to the universe's evolution. High-energy collisions might also produce exotic states of matter, such as quark-gluon plasma, which can provide additional context for understanding the transitions between different phases of matter in the early universe. Particle accelerators are vital tools for probing the conditions of pre-Big Bang physics. By recreating high-energy environments that reflect the universe's formative moments, these facilities allow scientists to test fundamental theories, explore unification of forces, and investigate the nature of matter and energy that shaped the universe. Through these efforts, researchers are gradually piecing together a more comprehensive understanding of the cosmos's origins and the mechanisms that govern its evolution. The anthropic principle raises intriguing questions when considering pre-Big Bang theories, primarily because it connects the fundamental properties of the universe to the existence of conscious observers like ourselves. The principle comes in two primary forms: the weak anthropic principle, which suggests that the universe's observed values are conditioned by the necessity for conscious beings to exist, and the strong anthropic principle, which posits that the universe must possess properties that allow for the emergence of life. When addressing the anthropic principle in the context of pre-Big Bang theories, it becomes essential to explore how initial conditions and physical constants influenced the development of a universe capable of supporting life. Many pre-Big Bang theories, such as those involving cosmic inflation or string theory, propose that a range of possible universes might exist, each with different fundamental parameters. This leads to the concept of a multiverse, wherein our universe is just one among many, each with distinct physical laws and conditions. In this framework, the anthropic principle helps explain why we find ourselves in a universe that appears finely tuned for life. It may simply be that we inhabit one of the few universes within the multiverse that supports life. By incorporating the anthropic principle, researchers can examine how specific pre-Big Bang conditions could have led to a universe with the necessary properties for life. For example, they might explore how certain asymmetries in the early universe, or variations in fundamental constants, could result in a habitable environment. Such discussions can help refine pre-Big Bang theories by identifying measurable predictions that can be tested against observational data. However, incorporating the anthropic principle also presents challenges. Critics argue that it introduces a form of circular reasoning, where the existence of observers is used to explain the universe's structure. Thus, while the anthropic principle can guide theoretical considerations, it must also be complemented by rigorous scientific exploration and empirical verification. This means ensuring that any pre-Big Bang theory inspired by the anthropic principle remains grounded in observable phenomena and can be rigorously tested. Ultimately, addressing the anthropic principle in the context of pre-Big Bang theories facilitates a broader understanding of the universe's origins. It encourages scientists to explore how initial conditions and potential multiverse scenarios could have influenced the fundamental properties we observe, allowing researchers to search for deeper connections between cosmology, theoretical physics, and the existence of conscious life. Current technology presents several limitations in probing the earliest moments of the universe, particularly those that occurred just after the Big Bang. One major challenge is the inability to access direct observational data from the very nascent universe itself, as it was obscured by a dense, hot plasma that only became transparent to radiation about 380,000 years after the Big Bang. Consequently, we are left to analyze indirect evidence, mostly through the cosmic microwave background radiation and the large-scale structure of the universe, which only give us a glimpse into the conditions of the universe's early moments. Another limitation is the energy scale needed to recreate conditions similar to those present during the early universe. The energies of particle interactions that characterize the moments after the Big Bang far exceed what current particle accelerators can achieve. While facilities like the Large Hadron Collider provide extensive data concerning high-energy processes, they may not yet be able to probe the extremely high-energy regimes associated with phenomena such as cosmic inflation or the unification of fundamental forces. Moreover, our current observational instruments are limited in their ability to detect more subtle signatures associated with the early universe. For instance, primordial gravitational waves generated during inflation are expected to carry critical information about the universe's formation. However, the sensitivity required to detect these waves is beyond what our current telescopes and detectors can achieve, particularly for very long wavelengths that would indicate inflationary processes. Upcoming missions may work towards improving this sensitivity, but until they are operational, our ability to investigate these early moments remains constrained. Additionally, theoretical frameworks continue to push the boundaries of our understanding of pre-Big Bang physics, but many of these theories lack definitive experimental verification. For instance, concepts such as string theory or loop quantum gravity present rich possibilities regarding the nature of space-time and the universe's origins, but remain largely untested in laboratory or observational settings due to the energy scales and environment they propose. Bridging these theoretical ideas with empirical evidence remains a significant challenge. While advancements in technology have enhanced our ability to explore the universe's origins, limitations in direct observation, energy scale capabilities, sensitivity to primordial signals, and empirical validation of theoretical models indicate ongoing challenges in probing the earliest moments of the universe. As scientific research progresses and new technologies emerge, it is hoped that these challenges will be addressed, expanding our understanding of the cosmos's fundamental beginnings. Dark matter plays a crucial role in our understanding of the universe's earliest states, providing insights into the structure and evolution of the cosmos shortly after the Big Bang. Although dark matter itself remains elusive and has yet to be directly detected, its presence is inferred from gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Understanding how dark matter interacts with other components of the universe helps illuminate the conditions that prevailed during its formative moments. In the earliest states of the universe, immediately following the Big Bang, the rapid expansion and cooling processes resulted in the formation of primordial particles. These particles included normal matter, protons, neutrons, and electrons, as well as dark matter particles, whose precise nature remains unknown but is widely believed to be non-baryonic and fundamentally different from the matter that makes up stars, planets, and beings like us. The interaction of dark matter with normal matter likely played a significant role in shaping the initial density fluctuations that would later evolve into galaxies and galaxy clusters. The significance of dark matter becomes particularly evident when examining the cosmic microwave background radiation. Fluctuations in this radiation provide a snapshot of the universe approximately 380,000 years after the Big Bang. Analysis of these fluctuations suggests that dark matter must have contributed to the gravitational wells that facilitated the clumping of regular matter, leading to the formation of the first structures in the universe. This interplay between dark matter and normal matter contributed to the universe's evolution, influencing the patterns we observe today. Furthermore, observations of large-scale structure reveal that dark matter governs the behavior of galaxies and galaxy clusters. The gravitational influence of dark matter helps to explain the rotational speeds of galaxies, which would otherwise be inconsistent with the observed distribution of visible matter. This influence provides vital clues about the matter distribution in the early universe and aids in reconstructing the timeline of cosmic evolution. Dark matter is integral to our comprehension of the universe's earliest states, influencing structure formation, density fluctuations, and the overall dynamics of cosmic evolution. By studying how dark matter interacts with normal matter and affects large-scale structures, researchers can glean valuable insights into the processes that occurred shortly after the Big Bang, enhancing our understanding of the fundamental forces that govern the cosmos. The distribution of galaxies offers vital clues about pre-Big Bang conditions, revealing insights into the processes that shaped the universe shortly after its formation. By analyzing how galaxies are arranged across the cosmos, scientists can infer the underlying structure and dynamics that governed the early universe. This investigation primarily stems from observing the cosmic web, a vast network of galaxies, clusters, and filaments that emerge from gravitational interactions influenced by dark matter. One significant aspect of galaxy distribution is that it reflects the initial density fluctuations that existed in the universe shortly after the Big Bang. When the universe became transparent to radiation approximately 380,000 years post-Big Bang, these fluctuations set the stage for gravitational collapse. Areas of slightly higher density would attract more matter, leading to the formation of galaxies and clusters. Thus, the observed cosmic structure today is a snapshot of the results of cosmic inflation and the subsequent evolution of these initial density fluctuations. Additionally, the large-scale distribution of galaxies provides valuable information about the expansion of the universe. The correlation between the clustering of galaxies and redshift measurements allows cosmologists to reconstruct the history of cosmic expansion and the influence of dark energy over time. By tracing back the positions of galaxies, researchers can model how gravitational interactions shaped the observable universe's large-scale structure, hinting at the laws of physics and conditions during the early universe. Moreover, studying galaxy distribution helps in understanding the role of dark matter. Galaxies tend to form along the edges of dark matter halos. The way these halos interact influences how galaxies cluster and distribute into larger structures. By mapping the distribution of galaxies, scientists gain insights into the underlying dark matter framework that played a crucial role in the formation and evolution of cosmic structures, reflecting the dynamics present in the pre-Big Bang state. Overall, the distribution of galaxies serves as a rich source of information regarding pre-Big Bang conditions. By simplifying the complexity of cosmic structure and evolution into observable patterns, researchers can glean crucial insights into the initial conditions that shaped the universe, as well as the fundamental laws governing its development. Each galaxy's position holds a piece of the puzzle that aids in reconstructing the early universe's history and the processes that drove cosmic evolution. The apparent fine-tuning of universal constants is a fascinating topic that speaks to the very nature of our universe. Before the Big Bang, the conditions and rules that governed the universe as we know it were not yet in place. However, pre-Big Bang theories propose that various factors could account for the specific values of these constants, which seem meticulously calibrated to allow for the existence of galaxies, stars, and life itself. One intriguing explanation comes from string theory, which posits that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. This theory suggests a framework in which the fundamental constants might arise from the shape and size of extra dimensions that we do not experience in everyday life. These extra dimensions could lead to a variety of possible constants through different configurations, hinting at a landscape of universes, each with its own set of rules. Another pre-Big Bang consideration is the concept of a multiverse. This theory posits that our universe is just one of countless others, each with varying constants and laws of physics. In such a multiverse, fine-tuning could be a result of natural selection among these universes. Only those that manage to develop the right conditions for structure formation and life would be observable to us, making our universe seem finely tuned when, in reality, it could simply be one of many. Additionally, there are models that focus on quantum gravity, suggesting that the universe might have undergone a transition before the Big Bang. In this view, classical physics and its constants might emerge from a more fundamental quantum realm. Variability in the constants during transitions could explain the fine-tuning we observe today, shifting the focus from mere coincidence to a deeper underlying framework of reality that remains to be fully understood. This interplay between theoretical frameworks and emerging evidence invites ongoing exploration into the very fabric of our cosmos. Pre-Big Bang theories profoundly challenge our conventional understanding of cause and effect, particularly because they propose a state of existence that lies outside the framework of time and space as we know it. In our daily lives, we observe a clear and logical sequence of events. Causes lead to effects, forming a chain of actions that makes sense. However, when considering the universe's beginnings, especially before the Big Bang, our familiar causal relationships become difficult to apply. One of the most compelling pre-Big Bang ideas is that of a singularity, a point where the laws of physics as we understand them break down. At this singularity, the traditional notions of time and space would not exist, meaning that the cause of the Big Bang itself could be fundamentally different from anything we can experience. Without time, the concept of causality loses its usual meaning, complicating our ability to trace back the origins of the universe in a linear fashion. Another intriguing aspect comes from theories related to quantum mechanics. In the realm of quantum physics, particles can exist in states that do not conform to classical cause and effect rules. Events may occur without a clear cause, or may even be influenced by factors we cannot yet fully observe. Pre-Big Bang models that incorporate quantum fluctuations suggest that the very fabric of the universe could generate spontaneous events, like the creation of matter, without the straightforward causal pathways we take for granted in our macroscopic world. Furthermore, considering a multiverse scenario also complicates cause and effect. If our universe is just one of many, the events that led to the Big Bang could have happened in a completely separate context, further distancing the cause from our observable condition. The multiverse invokes the idea that universes can pop into existence through quantum processes or mechanisms that do not adhere to the familiar rules of causality. This profound shift in perspective compels us to reevaluate our fundamental assumptions about the nature of existence, ultimately expanding the horizon of our understanding of the cosmos. Eternal universe models offer a radical shift in our understanding of creation, challenging traditional notions held for centuries. In contrast to the idea that the universe had a definitive beginning, such as the Big Bang, these models suggest that the universe has no starting point and instead exists in a perpetual cycle of creation and destruction. This perspective prompts a re-evaluation of what it means for something to be created, as it implies that the universe is eternal and self-sustaining. One prominent implication of eternal universe models is the notion that creation is not a singular historical event, but an ongoing process. For instance, cyclic models propose that the universe undergoes infinite cycles of expansion and contraction, where each cycle leads to a new stage of existence. This concept suggests that rather than seeking a moment of origin, one should look at the universe as a continuously evolving system where new formations and phenomena arise repeatedly. These models also invite philosophical and existential questions about purpose and meaning. If the universe is eternal and constantly regenerating, what does that imply for ideas of human existence and the significance of life's creation? The belief in an eternal universe could support a more holistic understanding of existence, one that emphasizes interconnectivity and dynamism rather than a linear trajectory that begins and ends. This perspective could reshape spiritual and philosophical beliefs surrounding the universe, prompting individuals to consider a deeper connection to a cosmos that has always existed in some form. Moreover, eternal universe theories impact our scientific inquiries as they encourage researchers to explore different physical laws and properties that govern an infinitely lasting universe. By examining the mechanisms behind perpetual change, scientists may uncover new insights into the nature of time, energy, and the ways in which cosmic structures evolve. Thus, the implications of these models extend far beyond cosmology, fostering a broader dialogue that intertwines science, philosophy, and spirituality as we seek to understand our place in this potentially endless universe. Pre-Big Bang theories present a fascinating intersection with various religious cosmologies, both aligning with and challenging traditional beliefs about the origin of the universe. Many religious narratives contain creation stories that describe a defined moment of creation, often attributed to a divine being or force. In contrast, pre-Big Bang theories tend to propose a universe that existed prior to a singular starting point, promoting concepts such as eternal existence or cyclical creation that can both complement and conflict with these spiritual views. For instance, some interpretations of ancient philosophies and religious traditions propose a universe that is eternal, echoing ideas found in Hindu cosmology, which describes an endless cycle of creation, preservation, and destruction. The cyclic models of the universe align well with these beliefs, suggesting that creation is not a one-time event, but an ongoing process of rebirth and transformation. This similarity allows for a potential dialogue between the scientific narratives of pre-Big Bang theories and certain spiritual interpretations, reinforcing the idea that the universe is a dynamic entity. On the other hand, many religious cosmologies, particularly those influenced by Judeo-Christian narratives, emphasize a clear beginning defined by an act of divine creation. Concepts such as creatio ex nihilo, which translates to creation out of nothing, position the universe as having a specific starting point, with creation expertly designed and executed by a divine power. Pre-Big Bang theories that suggest a universe existing in some form prior to our current conditions can challenge these beliefs, raising questions about the nature of the divine's role in creation and whether existence is dependent on an initial cause. Additionally, the implications of multiverse theories can further diverge from religious perspectives. This concept posits that multiple universes may exist with varying laws and constants, complicating the idea of a singular, purposeful act of creation. Such ideas may prompt discussions about the nature of divinity and the uniqueness of human existence. The exploration of pre-Big Bang models invites a rethinking of traditional cosmologies and encourages an ongoing conversation between science and faith, revealing how our understanding of the universe continues to evolve and challenge long-held beliefs about creation. The possibility of a multiverse brings forth a myriad of profound philosophical questions, challenging our understanding of existence, reality, and our place within it. One of the central inquiries revolves around the nature of reality itself. If multiple universes coexist with different laws of physics, constants, and even distinct histories, what does it mean for our understanding of what is real? The existence of parallel universes complicates our concept of uniqueness and originality. It forces us to rethink the significance of our experiences and choices within a potentially infinite array of alternatives. Another intriguing question involves the nature of existence and the criteria for defining life and consciousness. If a multitude of universes can host varying physical laws and conditions, how do we determine which realities foster sentient beings? This leads to the philosophical issue of whether life is a rare occurrence limited to our universe, or if it could be abundant across countless realities. Such implications could alter our understanding of consciousness, prompting discussions on whether forms of experience in other universes might differ drastically from our own, possibly challenging anthropocentric views of life. Additionally, the concept of free will comes into question within a multiverse framework. If every possible outcome exists across countless universes, does this diminish the significance of our choices? Are we merely participants in an elaborate web of outcomes that plays out in different realities, making personal agency seem insignificant. Alternatively, proponents of multiverse theories might argue that the existence of multiple outcomes underscores the importance of each decision we make, as every choice might lead to the spawning of new realities. Such discussions prompt a re-evaluation of moral responsibility and the weight of human decision-making. Lastly, considerations of purpose and meaning take on new dimensions within the context of a multiverse. If our universe is just one of many, and if life arises in various forms across different realities, what does this imply about humanity's role in the grand scheme of existence? Questions about purpose become complex and multifaceted, as individuals must contemplate whether meaning is assigned on a universal scale or emerges uniquely within each reality. This exploration not only challenges metaphysical beliefs, but also encourages a deeper investigation of our motivations and values within the broader tapestry of existence. Pre-Big Bang theories significantly influence our understanding of the universe's purpose, inviting a spectrum of interpretations regarding existence itself. Traditionally, many philosophical and theological perspectives assign a distinct purpose to the universe, often rooted in the belief that it was created by a divine entity with specific intentions. However, when examining pre-Big Bang models, which suggest that the universe could be eternal or exist in a state of perpetual change, the idea of purpose becomes more nuanced and complex. One perspective arising from pre-Big Bang theories is the notion that the universe's existence may not be contingent upon a predefined purpose or goal. Instead, the universe could be viewed as a dynamic system governed by natural laws and processes, where existence itself is an ongoing event rather than a goal-oriented outcome. This view challenges anthropocentric beliefs that place human existence at the center of a grand cosmic plan. In this context, life and consciousness emerge as phenomena within an evolving cosmic framework rather than as endpoints of a divine purpose. Furthermore, cyclic models propose that the universe undergoes infinite cycles of expansion and contraction. This perspective presents existence as a series of rebirths, potentially leading to the conclusion that purpose is fluid and changeable rather than fixed. In such a scenario, each cycle presents opportunities for different forms of structure, intelligence, and experience, further complicating the notion of a singular, overarching purpose. This evolving reality may invite individuals to create their own meanings within each cycle, fostering a more personal understanding of purpose as it relates to human experience. On the flip side, some interpretations of pre-Big Bang theories might encourage a renewed sense of wonder and exploration regarding the cosmos. The absence of a clearly defined purpose does not equate to a lack of significance. Rather, it opens up the space for curiosity and discovery. Individuals may find meaning in the pursuit of knowledge about the universe, in understanding its complexities, and in the relationships formed in the face of an expansive existence. This sense of agency in deciphering one's role in the universe can provide a powerful motivator, suggesting that individuals have the capacity to imbue their lives with purpose, even in a universe that may not adhere to a fixed teleological endpoint. Ultimately, pre-Big Bang theories compel us to reflect on our understanding of existence, encouraging diverse interpretations of purpose that align with an ever-expanding view of the cosmos. The implications of pre-Big Bang theories for the concept of free will are profound and multifaceted, as they invite us to reconsider the nature of choice, determinism, and the cosmos itself. At the heart of this discussion lies the relationship between the origins of the universe and the kind of agency humans possess. If the universe operates under laws that emerged from pre-Big Bang conditions, then it raises questions about whether our decisions are determined by these fundamental processes or if genuine free will exists independently of them. One significant consideration is the nature of causality itself. If pre-Big Bang models suggest that time and space as we understand them did not exist prior to the Big Bang, then the traditional chain of cause and effect becomes complicated. This could imply that our decisions could be influenced by factors beyond our comprehension, leading to a deterministic view where every action is the result of prior states. If free will is merely an illusion created by complex interactions within an overarching deterministic framework, it could challenge our understanding of personal responsibility and moral agency. Conversely, some interpretations of pre-Big Bang theories, particularly those that emphasize quantum mechanics, might offer room for free will to exist. Within the quantum realm, events can be probabilistic rather than strictly determined. If the universe is fundamentally indeterminate at its core, this uncertainty could provide a foundation for free will, allowing humans to make choices that are not rigidly bound by pre-existing conditions. In this view, individual agency may emerge as a complex interplay of deterministic laws and random quantum events, enabling a sense of autonomy in decision-making. Moreover, if we consider cyclic universe models, where the universe undergoes repeated cycles of expansion and contraction, this could suggest a bandwidth of possibilities for existence and choice. Each cycle could represent a new set of circumstances and paths that offer individuals the opportunity to make different decisions. In this light, free will might manifest as the ability to navigate choices within a dynamic framework, signifying that while there may be constraints imposed by the universe's structure, the potential for distinct experiences and decision-making ultimately exists. Ultimately, the interplay between pre-Big Bang theories and the concept of free will encourages an examination of the complexities of human experience. As we ponder the nature of agency within a potentially intricate and layered universe, we are led to contemplate the balance between determinism and freedom, inviting philosophical reflection on the responsibilities and capacities that come with our choices amidst a vast and mysterious cosmos. Pre-Big Bang models profoundly influence our perspective on the uniqueness of our universe by challenging the idea that our cosmos is a singular, exceptional creation. One significant implication of these models is the conceptualization of a multiverse, which posits that many universes may exist, each with its own physical laws, constants, and characteristics. This notion directly questions the singularity of our universe, suggesting that what we perceive as unique may be just one manifestation in a vast tapestry of realities. When considering cyclic models, which propose that the universe goes through endless cycles of expansion and contraction, the implications for uniqueness deepen. If our universe is merely one in a series of rebirths, then the attributes that we often view as special could be replicated or transformed in countless subsequent iterations. This viewpoint prompts a re-evaluation of how we perceive significant cosmic events, including the formation of stars, galaxies, and even life. Instead of seeing our universe's characteristics as rare, cyclic models invite us to think of them as part of a broader, ongoing cosmic process. Moreover, the quantifiable nature of eternal universe scenarios further enriches this dialogue about uniqueness. If the universe possesses an infinite timeline where every possible scenario could take place, then the singular circumstances of our existence might be just one occurrence among many potential realities. This expansive lens may diminish the sense of individual significance often attributed to our cosmos, underscoring the idea that many similar or even vastly different instances of existence might be unfolding elsewhere, either now or in the infinite future. However, this does not necessarily imply that the universe is devoid of significance or beauty. The recognition of multiple universes or cycles can also enhance the appreciation of our existence within a remarkable and perhaps serendipitous context. Understanding that our universe has the potential to share features with many others can invoke a sense of wonder and curiosity about what we can learn from it. Ultimately, while pre-Big Bang models challenge our perception of uniqueness, they also encourage a more profound exploration of existence, inviting us to appreciate our universe within a larger, intricate cosmic narrative. The various models of the universe's origin present compelling ethical considerations that invite reflection on our responsibilities, relationships, and understanding of existence. One notable consideration arises from the deterministic implications of certain models, such as those that suggest pre-Big Bang conditions lead to an inevitable unfolding of events. If our decisions are seen as determined by physical laws or the circumstances of the universe's creation, this challenges the concept of moral responsibility. Are individuals still accountable for their actions if every choice can be traced back to predetermined cosmic events? This issue provokes vital discussions about justice and accountability in a potentially deterministic world. Conversely, models that emphasize randomness and uncertainty, such as quantum mechanics, open up a framework for personal agency and ethical behavior. If choices can emerge from indeterminate conditions, individuals may have a greater sense of autonomy in shaping their destinies. This inherent freedom can elevate the ethical stakes associated with decision-making, encouraging a more profound consideration of the impact those choices have on oneself and others. The recognition that humans can influence the unfolding of events invites a collective responsibility to act ethically and thoughtfully in the face of countless possibilities. Additionally, multiverse theories raise ethical questions about the nature of existence and the value assigned to life. If numerous universes exist, each with different forms of life, this could influence how we view our own existence and the implications of actions taken in our universe. Are we morally obligated to consider the well-being of intelligences in other potential universes? While direct interaction may be impossible, this idea beckons us to think beyond anthropocentric perspectives, fostering a broader sense of ethical duty toward any sentient beings that could exist under diverse conditions. Lastly, the exploration of universe models raises broader ethical implications regarding scientific inquiry and technological advancements. As we deepen our understanding of the cosmos, ethical considerations about how this knowledge is used become paramount. Should emerging technologies informed by these theories be developed responsibly, with regard to the potential consequences they might have on our universe and beyond? The pursuit of knowledge about the universe must be accompanied by a commitment to ethical standards that prioritize the welfare of our planet, future generations, and the unknown lives that could exist elsewhere. Ultimately, these ethical dimensions compel us to consider how our understanding of the universe shapes not just our worldview, but also our moral framework as we navigate complex choices in an intricate and ever-expanding cosmos. The exploration of pre-Big Bang theories significantly impacts our understanding of consciousness and its relationship with the cosmos, inviting us to reconsider the nature of awareness within a broader cosmological context. One major implication lies in how these theories challenge the traditional notion of consciousness as a unique characteristic of human beings or life within a singular universe. If models such as the multiverse suggest infinite variations in physical laws and conditions, the potential for different forms of consciousness emerging across these various realities becomes an intriguing consideration. This expands the conversation about what consciousness is and how it may manifest in ways we cannot yet comprehend. Moreover, if pre-Big Bang scenarios indicate that our universe is just one iteration of many in an eternal or cyclical process, this raises questions about the continuity and evolution of consciousness. The Cyclic models propose that consciousness could arise repeatedly in different forms with each cycle. This concept suggests that consciousness is part of a larger process of existence, subject to the same dynamics that govern the universe: growth, decay, and rebirth. It prompts reflection on whether consciousness is transient or whether it carries over through different incarnations within the cycles of existence. This perspective can lead to a more interconnected view of self, promoting the idea that consciousness is not isolated but part of an ongoing cosmic interplay. Additionally, the incorporation of quantum mechanics within pre-Big Bang theories introduces the idea of consciousness as an active participant in the unfolding of reality. Some interpretations of quantum theory suggest that observation plays a critical role in determining the state of a system. If consciousness influences the behavior of particles at a fundamental level, this could indicate that awareness is not merely a byproduct of biological processes, but is intertwined with the very fabric of the universe. Such insight encourages a deeper exploration of the relationship between consciousness and physical reality, positioning awareness as a vital component in the ongoing story of the cosmos. Ultimately, pre-Big Bang theories compel us to reflect on the nature of consciousness as dynamic and inherently connected to the universe. By viewing consciousness through this expanded lens, we can appreciate it as a component of the larger cosmic narrative, prompting questions about the purpose, evolution, and potential of consciousness across different universes and experiences. This inquiry enriches our understanding of mind and existence, emphasizing the potential for greater wisdom and interconnectedness with the cosmos. The implications of pre-Big Bang theories for the long-term fate of the universe are both intriguing and complex, shaping our understanding of the ultimate destiny of cosmic structures and the very fabric of existence. Different models suggest a variety of scenarios regarding the universe's evolution, each with distinct consequences for its future. For instance, cyclic models propose that the universe goes through endless cycles of expansion and contraction. In this framework, each cycle ends with a cosmic rebound, leading to a new beginning. This suggests that rather than facing a definitive end, the universe may perpetually reinvent itself, fostering a sense of continuity and renewal. In contrast, theories that posit an eternal universe raise questions about the implications of infinite timelines. If the universe is eternal, it could potentially undergo various phases of development over inconceivable lengths of time. This scenario allows for continual transformation, where different structures and forms of matter could emerge, decay, and evolve well into the far future. The focus on an eternal universe invites contemplation of the nature of entropy, suggesting that while structures may dissipate over time, new configurations could accrue from the same fundamental building blocks, hinting at an ever-evolving cosmic landscape. Additionally, pre-Big Bang models influenced by thermodynamics raise the possibility of a universe that may ultimately face heat death, where all energy is evenly distributed and no thermodynamic processes can occur. In this scenario, the universe reaches a state of maximum entropy, resulting in a cold, dark expanse devoid of stars or active processes. This concept presents a rather bleak end, emphasizing the inevitable march towards balance and disorder. It challenges our understanding of vitality in the cosmos, pushing us to reflect on what sustained existence means in the face of entropy's long-term outcomes. Furthermore, explorations of cosmological constants and their role in the universe's fate, whether through expansion or contraction, underscore the uncertainty of ultimate outcomes. As researchers investigate these dynamics, the understanding of dark energy, dark matter, and their influences on cosmic evolution becomes crucial. The interplay of these forces could lead to divergent paths, whether toward a big crunch, where the universe collapses, or a big freeze, where expansion continues indefinitely. In each case, pre-Big Bang theories significantly impact our conceptualization of the universe's future, prompting profound questions regarding the nature of existence, the flow of time, and our place within the ongoing cosmic story, no matter how it unfolds. Differential geometry plays a crucial role in modeling the state before the Big Bang by providing the mathematical framework necessary to understand the curvature of space-time and the dynamics of the universe. This branch of mathematics focuses on the properties and applications of geometric structures, allowing scientists to express complex ideas about the fabric of space-time in a precise and rigorous way. When applied to cosmology, differential geometry helps to describe how the universe can warp and bend, ultimately leading to various theoretical models of its origins, including those that propose a pre-Big Bang state. In the context of general relativity, which describes gravity as the curvature of space-time, differential geometry allows researchers to formulate equations that govern how matter and energy influence the geometry of the universe. These equations can depict how space-time behaves under different conditions, including highly dense states that may have existed before the Big Bang. The use of differential geometry thus enables a deeper understanding of singularities, which are points in space-time where the gravitational field becomes infinitely strong, as well as regions where traditional physics breaks down altogether. Moreover, differential geometry facilitates the exploration of exotic theories about the universe's inception, such as string theory and loop quantum gravity. These models often rely on complex geometric structures that describe additional dimensions or quantum properties of space-time. By using differential geometry, scientists can analyze how these structures might interact or evolve, providing insights into possible pre-Big Bang scenarios that challenge conventional notions of time and space. Ultimately, the mathematics of differential geometry enriches our understanding of the universe's genesis and the conditions that may have prevailed just prior to the Big Bang. It brings together abstract mathematical concepts and physical theories, allowing for a comprehensive exploration of the relationships between space, time, geometry, and the fundamental forces of nature. This interplay between mathematics and physics is crucial for advancing our knowledge about the earliest moments of the cosmos and the potential states that existed long before our current understanding of the universe took shape. Topology plays a significant role in describing pre-universe conditions by offering a framework to understand the properties of space that remain invariant under continuous transformations. In the context of cosmology and theories related to the state before the Big Bang, topology helps to analyze the fundamental structure of the universe and its potential geometrical configurations. By investigating the topological features of spacetime, physicists can explore various scenarios regarding the universe's origins and evolution. One essential aspect of topology is its ability to categorize spaces based on their connectivity and dimensionality. In the pre-Big Bang context, researchers might investigate how different topological structures could lead to various kinds of universes. For instance, the idea of a universe with a non-trivial topology, such as a toroidal shape, can influence the paths of particles and the overall geometry of spacetime, affecting how the universe expands and evolves. Understanding these topological configurations provides insight into the fundamental characteristics of the early universe and informs models that attempt to describe its behavior. Furthermore, topology allows for the exploration of concepts like wormholes and other exotic structures that could facilitate connections between different regions of spacetime or even different universes. Such ideas remain speculative but are worth considering when investigating pre-universe conditions. By analyzing the topological properties of these hypothetical structures, scientists can explore the implications for causality, the flow of time, and the potential for quantum effects that might impact our understanding of both the Big Bang and what came before it. Additionally, topological concepts are instrumental in distinguishing between different phases of the universe's evolution. Topological transitions can occur when the universe undergoes phase changes, such as alterations in the symmetry or vacuum states that may impact the fundamental forces and particles that characterize the cosmos. By studying these transitions in relation to the conditions preceding the Big Bang, researchers can develop models that depict a more nuanced understanding of the universe's early states and the variety of pathways that could lead to the universe as we know it today. Overall, topology serves as a vital tool in expanding our comprehension of pre-universe conditions and their implications for the fundamental nature of reality. Quantum field theory plays a pivotal role in the study of the universe's origins by providing a framework that combines quantum mechanics with special relativity, enabling physicists to understand fundamental particles and their interactions in the early universe. This theoretical approach is essential for examining phenomena that occurred just after the Big Bang, as it allows researchers to explore the behavior of particles and fields at extremely high energies and densities. Applying quantum field theory to cosmology leads to significant insights regarding the conditions and dynamics of the universe's inception. One of the core contributions of quantum field theory to our understanding of the universe's origins is its ability to describe the behavior of fundamental particles as excitations of underlying fields. In the early universe, when temperatures were extraordinarily high, all known particles existed in a highly energetic state, and quantum fluctuations played a crucial role in shaping their interactions. By utilizing quantum field theory, scientists can model these fluctuations and establish how they contributed to the formation of the initial conditions necessary for the universe's expansion. Furthermore, quantum field theory introduces concepts like vacuum energy and spontaneous symmetry breaking, which are vital when considering the early universe. For instance, the mechanisms proposed by inflationary models, the rapid exponential expansion of space during the universe's infancy, rely on quantum field theory to describe how a scalar field, often referred to as the inflaton field, could drive this expansion. Understanding how vacuum energy associated with quantum fluctuations could lead to inflation provides insights into the very rapid growth of the universe, fundamentally altering its future evolution and structure. Additionally, quantum field theory allows researchers to investigate the interactions of various fields during the earliest moments of the cosmos. The interactions between different forces, such as electromagnetism, weak nuclear forces, and gravity, can be explored through the lens of quantum field theory. This enables physicists to probe the unification of forces at high energies and examine how they may have operated in a unified manner during the early universe, informing models that seek to understand the transition from this primordial state to the diverse structure we observe today. In summation, the application of quantum field theory to the study of the universe's origins provides powerful tools for comprehending the fundamental processes that shaped the cosmos. It allows scientists to delve into the dynamics of particle interactions in high-energy environments, explore the implications of inflationary scenarios, and draw connections between the fundamental forces that govern the universe's evolution, ultimately enhancing our understanding of how the universe came into being. To model the transition from pre-Big Bang to Big Bang states, physicists and mathematicians employ a range of advanced mathematical tools and frameworks. These tools facilitate the exploration of complex phenomena that occur during this crucial juncture in the universe's history, integrating concepts from various areas of mathematics and theoretical physics. One of the primary mathematical frameworks used is differential geometry, which helps describe the curvature of space-time. This is essential for understanding how gravitational forces influence the behavior of matter and energy in the context of the universe's expansion. The Einstein field equations, foundational to general relativity, are formulated within this framework, allowing researchers to explore the dynamics of space-time as it evolves from a singularity or highly dense state into the expanding universe we observe today. Another significant tool is the theory of dynamical systems, which investigates how systems evolve over time. This area of mathematics is particularly relevant when studying stability and instability in cosmological models. By applying dynamical systems theory, scientists can analyze how small fluctuations in the state of the universe could lead to dramatic changes, such as those seen in models emphasizing phase transitions or the dynamics of inflationary scenarios. This approach helps in understanding how the universe might transition from pre-Big Bang conditions to the highly energetic state that characterizes the Big Bang. Additionally, mathematical tools from quantum field theory play a pivotal role in exploring the fundamental particle interactions that could define the transition. Techniques such as perturbation theory and path integral formulation are vital for studying the behavior of quantum fields and their fluctuations in the early universe. These methods enable physicists to model the quantum processes at play, such as vacuum fluctuations, and their contributions to the conditions that led to the rapid expansion of the universe. Lastly, topology also provides valuable insights into the transitions that may occur in the universe. The study of topological properties can help in understanding the nature of phase transitions that might happen as the universe expands and cools, influencing how different forces and fields interact and manifest in the observable universe. By integrating these mathematical tools, researchers can construct comprehensive models that capture the complexity of the transition from pre-Big Bang states to the dynamic processes of the Big Bang, enhancing our understanding of the universe's origins and evolution. Non-commutative geometry emerges from the attempt to describe the fabric of spacetime at extremely small scales, particularly in the context of quantum mechanics and general relativity. At these levels, traditional notions of geometry based on smooth manifolds may not be adequate. Instead, non-commutative geometry provides a framework where spaces are defined not by points, but by algebraic structures. This concept has profound implications for understanding the early universe, especially moments immediately following the Big Bang. During those initial moments, the universe was incredibly dense and hot, with energies high enough that conventional geometry might break down. Here, non-commutative geometry suggests that space-time itself could have a fuzzy quality, where the very position of points is uncertain. This approximation of space leads to the idea that distances and spatial separations are not well defined. Instead, they are influenced by quantum uncertainties, which aligns with quantum field theory principles. Incorporating non-commutative geometry allows physicists to explore the behavior of various fundamental forces under those extreme conditions. It provides elegant scenarios for unifying quantum mechanics with gravity by redefining how we understand scale and interactions. Additionally, this geometric perspective has spurred theoretical frameworks such as string theory, where non-commutative features can be essential to reconciling gravity with other forces in nature. Researchers also leverage non-commutative geometry to analyze the evolution of forces and particles after the Big Bang, contributing to models that explain cosmic phenomena such as inflation and the distribution of galaxies. These theories can offer insights into the cosmic microwave background radiation and gravitational waves, helping us to probe the universe's early history and its fundamental nature beyond what classical physics predicts. Group theory plays a crucial role in understanding symmetries in pre-Big Bang physics, providing a mathematical framework to describe how physical systems behave under transformations. At the fundamental level, symmetries can reveal constants of nature and guide us in forming theories about the early universe. In the context of the pre-Big Bang scenario, where classical notions of time and space become blurred, group theory helps physicists explore the relationships between different forces and the particles that embody them. One of the central tenets of group theory is that every symmetry corresponds to a conservation law. For instance, when a system exhibits rotational symmetry, it implies that angular momentum is conserved. This principle extends to various interactions in the universe, including those governing the fundamental forces. When applying group theory to the early universe, scientists examine the symmetries associated with particle interactions and their significance in the formation of structure and evolution before the Big Bang. Particularly in models of the universe prior to the Big Bang, such as the ekpyrotic or cyclic universe theories, group symmetries help articulate behaviors of spacetime and energy as they interact in complex ways. For example, the transformations characterized by these groups can lead to mechanisms that drive cosmic potentials and scenarios without singularities. Here, the exchange between particles mediated by these symmetries can hint at pathways through which the universe may have transitioned into its current state. Additionally, understanding these symmetries can help physicists construct models that integrate quantum mechanics and general relativity. By leveraging group theory, researchers can investigate the unification of forces and ultimately contribute to a broader understanding of the conditions that might have existed before the Big Bang, as well as the nature of the universe's structure at its very essence. Mathematically modeling the concept of infinite density at the Big Bang singularity involves applying general relativity and the equations that govern the behavior of the universe. When physicists explore this singularity, they confront the limitations of our current scientific framework, where the equations of general relativity begin to break down under extreme conditions. A typical model to describe the early universe uses the Friedmann-Lemaitre-Robertson-Walker metric, which expresses a homogeneous and isotropic universe. As one turns back the clock to the moment of the Big Bang, models indicate that as the universe contracts, all matter and energy become concentrated into an infinitely small point. This leads to what we call a singularity, where density is considered infinitely high. In mathematical terms, this means that when one attempts to calculate the density by dividing mass by volume, both approaches yield a breakdown of the equations involved. Thus, instead of providing meaningful values, the equations yield infinities, signaling a point where our understanding of physics falters. Additionally, physicists utilize concepts from quantum mechanics, leading to theories that extend classical general relativity into quantum realms. Models based on loop quantum gravity suggest that space-time itself may be quantized, with no actual singularity existing because it inherently avoids infinite density. Instead, these models propose that a minimum length scale exists, providing new perspectives on density and space-time structure during the Big Bang. Therefore, while conventional mathematics predicts infinite density leading to a singularity, more advanced theories aim to provide a framework that can accommodate the dynamics occurring at these extreme states. By integrating insights from both general relativity and quantum mechanics, scientists continue to probe the nature of the universe at its origins, exploring models that might eventually lead to a coherent description of the conditions present at the moment of creation. Reconciliation of quantum mechanics and general relativity, especially during the early universe, is one of the most significant challenges in modern theoretical physics. Several mathematical frameworks are employed to address this complex interplay, each contributing unique insights aimed at understanding the conditions that prevailed shortly after the Big Bang. One prominent framework is string theory, which posits that fundamental particles are not point-like, but rather one-dimensional strings. This approach inherently incorporates both quantum mechanics and general relativity by requiring the unification of all forces in a higher dimensional space. String theory leads to a vast array of mathematical interpretations and structures, including the concept of extra dimensions, which can help explain phenomena like gravity, and unifying it with electromagnetism and the nuclear forces. These higher dimensions allow for a rich tapestry of potential interactions and offer possible resolutions to singularities. Another significant framework is loop quantum gravity, which attempts to quantize space-time itself. Unlike string theory, it does not rely on higher dimensions, but rather treats space and time as discrete entities that can be represented by quantized loops. This model suggests that at very small scales, space-time behaves like a network of interconnected loops, eliminating the singularity found in classical general relativity. By describing gravity in quantum terms, loop quantum gravity provides an alternative viewpoint on the early universe that avoids infinite quantities. Quantum field theory also plays a crucial role in these reconciliatory efforts. By developing a quantum version of gravity, physicists seek to formulate a self-consistent theory that incorporates gravitational effects into the framework of quantum mechanics. Approaches such as effective field theories examine low-energy limits of quantum gravity, allowing for predictions about early universe events, such as cosmic inflation and the production of particles in a rapidly expanding cosmos. Through the exploration of these frameworks, physicists aim to build a comprehensive understanding of the universe's origins, advancing toward a unified theory that can elegantly combine the principles of quantum mechanics with the geometrical insights of general relativity. Each approach offers valuable perspectives, contributing to the ongoing quest to decipher the mysteries of the cosmos. Applying concepts from information theory to pre-Big Bang models provides a novel perspective on the universe's evolution before its expansion. Information theory offers valuable tools for understanding how information is stored, transmitted, and processed within physical systems, which can be particularly insightful when analyzing early-state configurations of the cosmos. This approach shifts the focus from merely describing the universe in terms of matter and energy to considering the fundamental nature of information itself as a determining factor in cosmic events. One crucial concept from information theory is entropy, which denotes the amount of disorder or uncertainty in a system. In the context of the early universe, researchers explore how entropy behaves under conditions before the Big Bang. Some pre-Big Bang models propose that high entropy states may have governed the universe's conditions, leading to a homogeneous and isotropic universe emerging from a more complex and intricate informational structure. Understanding entropy allows physicists to analyze how moving from a high entropy state to a low entropy state, as seen in the universe's expansion, influences the formation of structures like galaxies. Moreover, in settings like loop quantum gravity, information theory can be employed to describe how quantum states are transformed as the universe evolves. It suggests that the universe's information content is conserved and fundamentally tied to the geometry of space-time. By interpreting the fundamental laws of physics as information processing algorithms, scientists can examine how quantum fluctuations may have influenced the transition from a pre-Big Bang state to the observable universe, focusing on how quantum states encode information about underlying structures. Finally, applying information theory to overall cosmological models encourages insights into how laws of physics could arise from more fundamental informational principles. Ideas such as holographic principles illustrate that the universe's three-dimensional information might be encoded on a two-dimensional surface. This concept not only deepens our understanding of gravity and quantum mechanics, but also proposes that the fabric of the universe is intricately woven from the threads of information, allowing physicists to hypothesize about the behavior and evolution of the universe before the Big Bang itself. Chaos theory plays a fascinating role in understanding the emergence of our universe by providing insights into how complex systems evolve from initial conditions that may seem simple or uniform. At the heart of chaos theory is the idea that small changes in initial conditions can lead to vastly different outcomes, a concept often referred to as the butterfly effect. This principle can be significant when applied to the early universe, where countless variables interacted under extreme conditions. In the context of cosmology, the dynamics of the universe during the moments following the Big Bang can be seen as a chaotic system. The universe's initial state, characterized by high temperatures and densities, set in motion a series of processes that were highly sensitive to their conditions. As the universe expanded and cooled, slight fluctuations in density led to the formation of galaxies, stars, and larger cosmic structures. Understanding these processes through chaos theory allows scientists to model how diverse and intricate patterns could emerge from what initially may have appeared as a homogeneous state. Moreover, chaos theory contributes to the study of cosmic inflation, a rapid expansion of space that occurred shortly after the Big Bang. The inflationary framework suggests that quantum fluctuations during this period can generate density variations, which are essential for the large-scale structure of our universe. In this sense, chaotic dynamics can help describe how these fluctuations evolve and influence the distribution of matter. Thus, chaos theory not only clarifies the behavior of systems in the early universe, but also helps theorists comprehend how randomness can lead to the order seen in cosmic structures today. Additionally, researchers increasingly explore connections between chaos theory and quantum mechanics, potentially offering a deeper understanding of how quantum uncertainties might contribute to chaotic behavior at a cosmic scale. This intersection emphasizes the complexity of the universe's development, suggesting that robust patterns of structure can arise amid apparent randomness. Through the lens of chaos theory, the emergence of our universe becomes a tale of unpredictable interactions and complex behaviors, highlighting both the intricate nature of cosmic evolution and the subtle laws that govern it. Understanding pre-Big Bang physics has the potential to significantly influence future energy technologies by offering insights into the fundamental nature of energy, matter, and the underlying structures of the universe. At the heart of this exploration lies the search for unified theories that bridge quantum mechanics and general relativity, which can reveal new principles governing energy interactions. Such discoveries may lead to transformative breakthroughs in harnessing and utilizing energy resources more efficiently. One promising avenue is the investigation of quantum field theories and their implications for energy production. Concepts developed during the study of early universe conditions, such as the dynamics of quantum fluctuations and vacuum energy, may inform new methods for energy extraction. For instance, if physicists can better understand how these fluctuations operate, they may devise technologies that tap into zero-point energy, which refers to the energy present even in a perfect vacuum. Harnessing this form of energy could revolutionize power generation. Additionally, examining pre-Big Bang physics may unveil novel materials and energy systems inspired by the extreme conditions that existed in the early universe. Research into materials with exceptional properties, informed by insights from high-energy physics, could lead to advancements in superconductors or energy storage solutions. These developments could enable lossless energy transmission and vastly improved battery technology, contributing to cleaner and more efficient energy use across various sectors. The study of pre-Big Bang dynamics can also inspire innovative approaches to understanding fusion reactions. By examining how matter behaved under radically different conditions, researchers could uncover new pathways to achieve sustainable nuclear fusion, a potential source of virtually limitless energy. Understanding the fundamental interactions at these energetic scales could guide experimental designs for fusion reactors and improve prospects for energy independence. Through these avenues, the insights gleaned from pre-Big Bang physics may not only enhance our comprehension of the cosmos, but also have profound implications for technological advancements. By integrating fundamental science with practical applications, humanity's quest for clean, sustainable energy could be dramatically transformed. Harnessing principles of quantum vacuum fluctuations could lead to a range of innovative applications across various fields, particularly in energy production, telecommunications, and advanced materials. Quantum vacuum fluctuations refer to the transient changes in energy that occur in empty space due to the uncertainty inherent in quantum mechanics. By understanding and manipulating these fluctuations, scientists and engineers could unlock new technologies. One of the most discussed potential applications is the possibility of tapping into zero-point energy. This energy exists in the ground state of quantum fields and, if effectively harnessed, could provide a nearly limitless energy source. Although technically challenging, the implications of such a breakthrough would be monumental. Harnessing zero-point energy could lead to clean, efficient power generation, eliminating reliance on fossil fuels and other finite resources, thus helping mitigate climate change and promote sustainability. Another exciting application involves advancements in quantum computing. Quantum vacuum fluctuations can influence the behavior of qubits, the fundamental building blocks of quantum computers. By controlling these fluctuations, researchers may enhance the performance and stability of quantum systems, leading to more powerful and efficient quantum processors. This could accelerate advancements in algorithms that solve complex problems across various domains, from cryptography to optimization challenges in logistics and finance. Additionally, principles related to vacuum fluctuations could pave the way for novel materials with unique properties. For instance, engineered materials may exhibit enhanced electromagnetic properties by exploiting these fluctuations. This could yield advancements in areas such as superconductor technology and sensors, enabling devices that operate with minimal energy loss or greater sensitivity than current technologies allow. In telecommunications, understanding and manipulating quantum vacuum effects could also lead to the development of ultra-secure communication systems. Quantum key distribution exploits quantum principles to create secure information channels, making it nearly impossible for eavesdroppers to intercept communications without detection. By leveraging vacuum fluctuations in quantum communication protocols, researchers could create networks that enhance security in data transmission, which is increasingly crucial in our digitally connected world. Overall, the potential applications that could arise from harnessing principles of quantum vacuum fluctuations represent a fascinating intersection between theoretical research and practical technology, with implications that could transform energy usage, computing, material science, and secure communications. Insights into the nature of time before the Big Bang could profoundly influence computing technologies by changing our understanding of information processing, quantum mechanics, and the fundamental principles of computation itself. The exploration of time in cosmological contexts, particularly in frameworks that redefine or alter classical notions of time, opens new avenues for developing advanced computing models and architectures. One significant impact could arise from the investigation of quantum time and its relationship to information. An improved understanding of how time operates at quantum levels may lead to the development of quantum computing technologies that are faster and more efficient than existing systems. Specifically, if researchers can navigate the implications of time's behavior in pre-Big Bang scenarios, they could unlock novel quantum algorithms that leverage temporal dynamics, allowing computers to perform computations in ways that classical systems cannot. Additionally, exploring the concept of time as a fundamental feature of the universe could inspire new models of computation that take advantage of nonlinear or higher dimensional time scenarios. For instance, in models where time behaves differently from the linear progression we typically experience, computations could integrate multiple states simultaneously. This might pave the way for new paradigms in data processing and storage, wherein systems could exploit these complex temporal frameworks to access and process vast amounts of information with reduced latency. Insights on the continuity of time or its potential for cyclical behaviors could also motivate innovative designs in networked computing. Systems that collaborate over time, drawing on distributed data from multiple nodes, might evolve to synchronize their operations more effectively, improving scalability and resilience. These concepts can lead to more robust frameworks in cloud computing and decentralized networks, enhancing efficiency and security. Finally, as researchers further explore the connections between time, entropy, and information theory, the relationship between these elements could yield insights into improving error correction techniques and developing more reliable information transmission mechanisms. By integrating concepts from cosmology into the foundations of computing, scientists could enhance the resilience of systems against disruptions, ensuring data integrity. Overall, an understanding of time before the Big Bang could inspire transformative advances in computing technologies, spurring new approaches to quantum information processing, temporal architectures, and networked systems, ultimately reshaping how we conceive of computation in both theoretical and practical terms. Pre-Big Bang theories offer intriguing implications for space exploration and propulsion by providing new insights into the fundamental nature of space-time and the fabric of the universe. Understanding the conditions and dynamics that may have existed before the Big Bang could inspire innovative approaches to traveling beyond our solar system and developing advanced propulsion technologies. One exciting direction arises from exploring concepts such as vacuum energy and quantum fluctuations, which have been subjects of intense study in cosmology. If researchers can successfully harness vacuum energy or understand how to manipulate the fabric of space-time based on pre-Big Bang dynamics, it may lead to revolutionary propulsion systems. For instance, concepts like the Alcubierre warp drive, which theoretically allows for faster-than-light travel by contracting space in front of a spacecraft and expanding it behind, could become more feasible with a deeper understanding of how space behaves under extreme conditions. The study of pre-Big Bang conditions might also lead to advancements in understanding gravity and gravitational waves. Insights gained could inform technologies that leverage gravitational effects for propulsion. For example, a better grasp of manipulating gravitational fields could facilitate novel methods for spacecraft propulsion, potentially making interstellar travel more achievable. These concepts might help develop systems that operate on principles not constrained by conventional physics, allowing humanity to explore distant galaxies. Additionally, some pre-Big Bang theories incorporate ideas about the cyclical nature of the universe. This perspective could inform mission planning for long-term space projects, suggesting that certain energy environments or gravitational anomalies might allow for repeatable pathways or shortcuts through space. This understanding could influence navigation and exploration strategies, optimizing routes for missions to the outer planets or beyond. Finally, innovations in understanding dark energy and its role in cosmic expansion could lead to technologies designed to harness or mitigate its effects. If scientists can decode the interplay of dark energy with pre-Big Bang dynamics, they might develop new methods for stabilizing spacecraft against the accelerating expansion of the universe and devising ways to navigate through it. Insights gleaned from pre-Big Bang theories hold the potential to inspire groundbreaking advances in propulsion technology and strategies for space exploration, opening up new avenues for humanity's journey into the cosmos and fundamentally altering our approach to traversing the universe. Understanding the fabric of pre-universe existence can significantly influence materials science by offering insights into the fundamental properties of materials at extreme conditions and leading to the development of novel substances with unique characteristics. As researchers explore theories surrounding the early universe, they uncover potential frameworks that can guide the design and synthesis of materials that perform exceptionally well in demanding environments. One key area of influence stems from studying the high-energy states that may have existed prior to the Big Bang. These conditions could inspire the creation of materials that can withstand extreme temperatures and pressures akin to those found in stellar interiors or during high-energy collisions. By replicating these conditions in laboratory settings, scientists could discover or engineer materials with remarkable resilience, durability, and thermal properties, potentially revolutionizing sectors such as aerospace engineering, energy storage, and electronic devices. Insights derived from quantum fluctuations and vacuum energy could also shape materials science. By understanding how vacuum states interact with matter, researchers may develop materials that exploit quantum effects to achieve superior conductivity or magnetism. This could lead to transformative advancements in superconductors, which operate with little to no resistance, allowing for more efficient electrical transmission and applications in high-speed computing and advanced magnetic resonance imaging technologies. Additionally, pre-universe existence theories can influence the study of complex systems and emergent properties. These insights may guide the design of smart materials that respond dynamically to their environment, adapting their properties under different stimuli. This could have applications in fields such as soft robotics, where materials must change shape or stiffness in response to external conditions, or in developing responsive coatings that protect surfaces from wear or corrosion. The exploration of space-time dynamics and the interplay between fundamental forces could also inspire new approaches to metamaterials, which gain exotic properties through engineered structures rather than traditional compositions. Insights from cosmological models may inform the design of materials that manipulate light or other wave phenomena in unprecedented ways, leading to innovative applications in optics and communications technologies. Overall, the understanding of the fabric of pre-universe existence has the potential to drive significant advancements in materials science, leading to the development of superior materials with enhanced capabilities and functionalities, ultimately transforming various industries and enhancing technology's role in society. A deeper understanding of fundamental physics holds significant promise for advancing medical applications, with potential benefits across diagnostics, treatment methods, and the development of new technologies in healthcare. By bridging concepts from physics with medical science, researchers can innovate techniques that enhance patient care and improve health outcomes. One of the most impactful areas is in medical imaging. Advances in understanding quantum mechanics and particle physics have already led to techniques like positron emission tomography and magnetic resonance imaging. Continued research into the fundamental properties of matter may allow for the development of even more sophisticated imaging technologies. For instance, improved understanding of how particles interact at subatomic levels could enhance imaging precision, leading to earlier detection of diseases such as cancer and allowing for more accurate monitoring of treatment efficacy. Moreover, insights into various fundamental forces and interactions could lead to innovative radiation therapies. By exploring the interactions of high-energy particles with biological tissues, researchers can develop new techniques to target cancer cells more effectively while minimizing damage to surrounding healthy tissue. This could pave the way for more refined approaches to radiation treatment, yielding improved patient outcomes and fewer side effects. Quantum mechanics also underpins the development of novel drug delivery systems. By leveraging principles of quantum information and materials science, researchers may engineer drug delivery mechanisms that respond dynamically to specific physiological conditions. For example, nanoparticles designed to release therapeutic agents only in the presence of certain biomarkers could enhance the efficacy of treatments while reducing systemic side effects. Additionally, fundamental physics can contribute to the field of biophysics and the understanding of complex biological systems. By applying physics-based modeling approaches to biological processes, scientists can investigate phenomena such as protein folding or cellular interactions on a deeper level. Insights gleaned from these studies could inform the development of targeted therapies and personalized medicine strategies that align with an individual's unique biological makeup. Lastly, developments in physics can also enhance technologies for biomedical devices. Improved understanding of materials, quantum phenomena, and thermal dynamics can lead to more effective sensors for monitoring vital signs, advanced prosthetics, and innovative diagnostic devices that provide real-time feedback to healthcare providers. Overall, the convergence of fundamental physics with medical applications opens a realm of possibilities that could revolutionize healthcare, enhance diagnostics, refine treatment methodologies, and facilitate the development of next-generation biomedical technologies. Pre-Big Bang theories could significantly influence the development of quantum computing by providing novel insights into the fundamental principles of information processing, quantum states, and the nature of reality itself. As researchers explore the conditions that may have existed before the Big Bang, they uncover concepts that could reshape our understanding of quantum mechanics and lead to advancements in quantum technologies. One critical area of influence pertains to the fundamental understanding of quantum states and their interactions. Pre-Big Bang models often involve high-energy physics scenarios where quantum fluctuations could play a substantial role. By studying how quantum states behaved under these extreme conditions, scientists may gain insights that lead to the development of more robust qubits, the essential building blocks of quantum computers. Improved qubit designs informed by these theories could enhance coherence times, reduce error rates, and enable more efficient quantum operations. Furthermore, concepts from pre-Big Bang theories can contribute to our understanding of non-locality and entanglement, two phenomena central to quantum computing. The exploration of how quantum information might have been processed or transferred in the early universe could inspire new protocols for quantum communication and secure information transfer. This could enhance the capabilities of quantum networks, leading to advancements in cryptography and secure data transmission. Additionally, researching the connection between gravity and quantum mechanics, as suggested by some pre-Big Bang theories, could inform the development of quantum gravity models that reconcile general relativity with quantum principles. If successful, these insights could open up new avenues for building quantum computers that can operate in ways not traditionally considered, potentially leading to innovative architectures that outperform current designs. Moreover, the exploration of the concepts of time and space in pre-Big Bang conditions may lead to new models of quantum computing that take advantage of multidimensional time or different temporal frameworks. Such innovations could change our approach to quantum algorithms and computation speed, making it possible to process information in ways that classical systems cannot match. The interplay between pre-Big Bang theories and quantum computing could yield transformative advancements, enhancing our understanding of quantum states, improving computational techniques, and potentially leading to entirely new paradigms for harnessing quantum mechanics in computation. This exploration may ultimately contribute to making quantum computing technologies more accessible and practical for a range of applications. Understanding fundamental physics, particularly insights gained from pre-Big Bang theories and quantum mechanics, has profound implications for the future of communication technologies. These advancements could reshape how information is transmitted, secured, and processed across vast distances, leading to substantial improvements in efficiency and security. One of the most exciting implications lies in the realm of quantum communication. By leveraging principles such as quantum entanglement and superposition, researchers are developing quantum key distribution systems that can create secure communication channels. Unlike classical encryption methods, which can be vulnerable to hacking, quantum communication protocols utilize the laws of quantum mechanics to ensure that any attempt to intercept the information will be detectable. This capability could revolutionize areas such as banking, national security, and data privacy, enabling ultra-secure communication networks. Additionally, insights from quantum mechanics may pave the way for the realization of quantum networks, where quantum bits, qubits, are interconnected similarly to classical networks. These quantum networks could potentially facilitate the transmission of information that is exponentially faster than current methods. This leap in speed and efficiency could enable a new era of telecommunications, where real-time communication across previously unbridgeable distances becomes possible, fostering global interconnectivity. Furthermore, exploring the nature of time from pre-Big Bang perspectives could inspire novel ideas for temporal communication. If researchers uncover ways to manipulate the dimensions of time, they may enable systems that can send information backward, creating methods of communication that challenge our conventional understanding of causality. While this concept seems speculative, it highlights how fundamental physics could provoke radical changes in our communication paradigms. Moreover, understanding fundamental physical principles could lead to advancements in the development of materials used in communication technologies. Quantum dots, photonic crystals, and other advanced materials whose properties are informed by fundamental physics might improve the efficiency of optical fibers and telecommunications equipment, resulting in more durable systems with enhanced signal clarity. The implications of these advancements extend beyond telecommunications. They touch on the foundational aspects of how we interact with technology. As communication technologies evolve under the influence of quantum mechanics and fundamental physics, they could redefine personal interactions, enable smarter networking systems, and enhance our ability to share information in an increasingly interconnected world. Overall, the impact on communication technologies could be transformative, leading to secure, instantaneous, and potentially revolutionary ways to connect. Theories emerging from fundamental physics, particularly insights derived from pre-Big Bang scenarios and quantum mechanics, could significantly impact our approach to environmental and climate sciences. By enhancing our understanding of the universe's fundamental principles, these theories may inform innovative strategies for addressing climate change, optimizing resource use, and developing sustainable technologies. One potential area of impact lies in energy generation and storage. By applying concepts from fundamental physics, researchers may develop new energy technologies that harness previously unexplored sources, such as vacuum energy derived from quantum fluctuations. If scientists can successfully tap into these energy sources, it could lead to clean, sustainable power generation that significantly reduces dependence on fossil fuels and lowers greenhouse gas emissions. This shift could play a crucial role in mitigating climate change and transitioning to a more sustainable energy infrastructure. Furthermore, knowledge gained from studying the fundamental interactions between particles and forces in extreme conditions could inform the advancement of carbon capture and storage technologies. Understanding how gases interact at quantum levels could lead to more efficient methods of capturing carbon dioxide from the atmosphere or industrial processes, enhancing efforts to lower atmospheric concentrations and combat climate change. Additionally, the exploration of physical principles related to complex systems may enhance our understanding of ecological interactions and climate dynamics. By applying physics-based modeling approaches to natural systems, scientists can better simulate climate models, predicting more accurately how various factors, such as temperature, humidity, and atmospheric pressure, interact within the Earth's climate. Improved models can provide invaluable insights for policymakers and researchers to devise effective strategies for adaptation and mitigation. Moreover, advancements in materials science driven by fundamental physics could lead to the development of new materials with superior properties for environmental applications. For instance, researchers may create advanced materials that enhance the efficiency of solar panels, improving energy conversion rates and making solar power more viable as a primary energy source. Novel materials could also minimize waste in manufacturing processes, contributing to a circular economy and reducing the environmental impact of industrial activities. Lastly, lessons learned from fundamental physics about the interconnectedness of systems could inform more holistic approaches in environmental and climate sciences. Recognizing how various ecological, atmospheric, and human systems influence each other can lead to integrated strategies that address multiple facets of environmental challenges, ensuring that efforts to combat climate change consider social, economic, and ecological dimensions. The integration of theories from fundamental physics into environmental and climate sciences can lead to groundbreaking innovations and approaches, enhancing our capacity to address and adapt to the pressing challenges posed by climate change while fostering sustainable development and resilience. Technologies inspired by pre-Big Bang physics, while offering transformative potential, also raise a variety of risks and ethical concerns that must be meticulously considered. As researchers explore and develop innovative applications grounded in these complex theories, awareness of the implications of such technologies becomes paramount. One significant risk involves the misuse of advanced technologies, particularly in fields like quantum communication or energy generation. For instance, if quantum encryption methods are misappropriated, it could lead to unprecedented levels of secure communication that might be exploited by malicious actors for illegal purposes, such as cyber warfare or espionage. Additionally, harnessing vacuum energy or similar concepts improperly could pose unforeseen dangers, potentially destabilizing established energy systems and leading to unpredictable consequences for our power infrastructure. Another ethical concern centers on equity and access. As technologies inspired by fundamental physics develop, there is a risk that the benefits may not be distributed equitably across different populations. Innovations in energy generation, for instance, could be costly to develop and implement, leading to disparities between wealthy nations and developing countries. Ensuring that advancements in technology contribute to social good rather than exacerbating existing inequalities is a crucial ethical consideration. The potential impact of these technologies on the environment also warrants scrutiny. While many innovations aim to address environmental issues, the unintended consequences of deploying new technologies can be significant. For example, energy extraction methods derived from quantum mechanics may have unforeseen effects on ecosystems or contribute to resource depletion. Conducting thorough assessments of ecological impacts is essential to prevent harm while ensuring that technological progress aligns with environmental sustainability. Moreover, the rapidly evolving nature of the technologies inspired by pre-Big Bang physics raises questions about regulatory frameworks and governance. Current policies may not be adequately equipped to address the ethical implications of advanced quantum technologies or novel energy systems. As such, establishing comprehensive regulations that prioritize safety, ethical usage, and responsibility is vital to mitigating risks associated with emerging technologies. Lastly, the frontiers of fundamental physics often touch on concepts regarding the nature of reality, consciousness, and the universe's origins. As research progresses, philosophical and ethical questions about existence itself may arise, altering human perceptions and beliefs. Engaging in discussions that bridge science, ethics, and philosophy becomes crucial to navigating these debates thoughtfully and respectfully. In conclusion, while the exploration of technologies inspired by pre-Big Bang physics holds incredible promise, addressing the associated risks and ethical concerns is essential to ensure that such advancements are implemented in ways that enhance human well-being, promote equity, and protect the environment. Concepts from biology, particularly the idea of emergence, provide a fascinating lens through which to explore the origin of the universe. Emergence refers to the process by which complex systems and patterns arise from the interactions of simpler components. This principle can illuminate our understanding of how the universe evolved from an incredibly dense and homogeneous state into the vast, complex cosmos we observe today. In the context of cosmology, the early universe is often described as being in a state of high energy and uniformity. As it expanded and cooled, small fluctuations occurred at quantum levels, leading to slight variations in density. These minute differences can be likened to the components of a biological system where individual interactions give rise to larger, coherent patterns. The concept of emergence helps explain how such tiny fluctuations eventually led to the formation of galaxies, stars, and planetary systems, highlighting the transition from simplicity to complexity over time. Furthermore, understanding emergence in biology can inform the study of self-organization within the universe. Similar to how biological systems, like flocks of birds or cellular structures, can develop intricate patterns without central control, the universe exhibits self-organizing behavior on a cosmic scale. Gravitational interactions among matter can lead to the formation of large structures, such as galaxies and galaxy clusters, from the primordial chaos. This process emphasizes how fundamental forces and simple interactions can yield sophisticated structures and systems in both biology and cosmology. Additionally, concepts of emergence in biology raise intriguing questions about the nature of life itself and its place within the universe. If we consider the universe to be a complex system, the emergence of life may be viewed as one of its many outcomes. The study of complex adaptive systems in biology, which includes ecosystems and evolutionary processes, can provide insights into how life's emergence reflects underlying physical laws and cosmic dynamics. Moreover, interdisciplinary approaches that blend insights from biology, physics, and philosophy can expand our understanding of both the universe's origin and the emergence of consciousness. By examining how individual and collective behaviors arise in varying contexts, scientists may develop a richer understanding of how conscious beings relate to the cosmos and how the universe itself may harbor forms of information processing or consciousness at different scales. Concepts like emergence from biology enrich our understanding of the origin of the universe by highlighting the complex interplay of fundamental processes that lead to the formation of intricate structures and systems. This perspective fosters a more integrated view of the cosmos and life's place within it, encouraging explorations that span across disciplines to deepen our comprehension of existence. Neuroscience can provide significant insights into our ability to comprehend abstract concepts like nothingness and the early universe by exploring how the brain processes complex ideas, constructs understanding, and interprets experiences. As humans grapple with these profound philosophical and scientific notions, insights from neuroscience offer explanations for the cognitive mechanisms involved. One key aspect of this exploration is how the brain makes sense of the idea of nothingness, a concept that challenges our traditional understanding of existence. Neuroscientific research reveals that the human brain is not naturally inclined to comprehend the absence of something. Instead, it tends to fill gaps with context-rich interpretations based on sensory experiences. This tendency is rooted in our evolutionary need to navigate the physical world, which shapes our perceptions and cognitive frameworks. The brain's reliance on context means that grappling with the concept of nothingness often leads to abstract thinking that can evoke feelings of uncertainty or discomfort. Additionally, understanding the neural basis of abstract thought can shed light on how individuals conceptualize the early universe, which encompasses vast scales of time and space, as well as conditions that seem entirely foreign to human experience. Neuroscience has identified brain regions involved in reasoning, imagination, and spatial cognition, such as the prefrontal cortex and parietal lobes. These areas are engaged when individuals attempt to construct mental models of cosmic phenomena or visualize temporal scales beyond everyday experiences. The brain's ability to create and manipulate abstract representations allows for the formulation of hypotheses and ideas about the universe's origins, even if those concepts remain outside direct observation. Moreover, the concept of cognitive elasticity plays a pivotal role in how we adapt our understanding of complex topics like the early universe. Neuroplasticity, the brain's ability to reorganize itself in response to learning and experience, facilitates the incorporation of new scientific insights into existing mental frameworks. As our knowledge of physics and cosmology expands, individuals can reshape their understanding of the universe and its initial conditions, accommodating more sophisticated models and theories. Furthermore, exploring the philosophical dimensions of neuroscience can illuminate how concepts of nothingness and the origin of the universe intersect with existential questions about consciousness, perception, and reality. These explorations may lead to deeper reflections on the human condition and existential experiences, further enriching the discourse surrounding the nature of existence and non-existence. Neuroscience offers valuable insights into our ability to comprehend nothingness and the early universe by examining how the brain processes abstract concepts, constructs mental models, and adapts to new knowledge. This understanding bridges cognitive science with philosophical inquiries and provides a framework for exploring the nature of existence, ultimately enhancing our appreciation of the profound mysteries of the cosmos. Psychological concepts of perception can significantly influence our theories about pre-Big Bang states by shaping how we interpret and conceptualize the universe's origins. Perception, fundamentally rooted in human cognition, not only dictates how we experience reality, but also influences the frameworks we use to understand abstract concepts that lie beyond direct observation, such as the conditions before the Big Bang. One of the key psychological aspects is how human perception is limited by sensory experience. Our brains have evolved to interpret information based on immediate physical encounters and relationships in the three-dimensional world. When theorizing about the pre-Big Bang state, which might involve dimensions or conditions that transcend our sensory limitations, scientists must rely on abstract reasoning and analogies. This reliance can shape the formulation of theories about the early universe by framing complex phenomena in terms that are more relatable, potentially leading to interpretations that align more closely with our perceptual experiences rather than strictly aligning with scientific rigor. Additionally, cognitive biases inform how scientists engage with abstract cosmological concepts. For example, the human tendency toward teleological thinking can influence our interpretations of the pre-Big Bang state. This bias may lead us to ascribe purpose or direction to the formation of the universe, which might not reflect the underlying physical principles at play. Such biases can shape theoretical narratives and influence the acceptance of certain models over others, thereby impacting the direction of research and exploration in cosmology. Moreover, our understanding of ambiguity and uncertainty from a psychological perspective plays a crucial role in interpreting pre-Big Bang theories. Human cognition often struggles with ambiguity, leading to attempts to create order out of chaotic or undefined concepts. In the context of the early universe, where initial conditions may be poorly understood or radically different from our everyday experiences, this tendency can result in an inclination towards deterministic models that promise clarity. Advances in theoretical physics require balancing this quest for understanding against the inherent uncertainties associated with such complex concepts. Furthermore, the collaborative nature of scientific exploration can also be influenced by psychological perceptions. The way in which theories about the pre-Big Bang state are communicated and understood within the scientific community can affect collaboration and the synthesis of ideas. The influence of group dynamics, social validation, and consensus can lead to the normalization of certain theories while marginalizing alternative viewpoints. This dynamic is crucial as it shapes the research landscape and influences which theories gain prominence. Psychological concepts of perception significantly influence theories about pre-Big Bang states by shaping our interpretations of complex and abstract phenomena. The limitations of human cognition, cognitive biases, reactions to uncertainty, and collaborative dynamics all contribute to the frameworks through which we understand the origins of the universe, ultimately influencing the directional flow of research in cosmology. Parallels between cosmic evolution and biological evolution reveal fascinating similarities in the processes that govern the development of complexity in both the universe and life on Earth. By examining these shared characteristics, we can gain a deeper understanding of how intricate structures emerge in vastly different contexts. One of the most striking parallels is the idea of gradual change through incremental steps. In cosmic evolution, the universe began with the Big Bang and has since expanded, cooled, and evolved through various stages, from the formation of subatomic particles to the creation of stars, galaxies, and eventually complex structures like planetary systems. Similarly, biological evolution operates through gradual changes in species over time, driven by genetic mutations and natural selection. Both processes illustrate a journey from simple beginnings to increasingly complex forms, emphasizing that complexity can arise incrementally from simpler components. Another significant parallel lies in the role of randomness and chaos in both cosmic and biological contexts. In the universe, quantum fluctuations in the early universe can influence the distribution of matter, leading to the formation of large-scale structures and determining the paths of cosmic evolution. In biology, genetic mutations occur randomly and can produce variations among organisms, some of which may confer advantages in specific environments. In both scenarios, randomness introduces variability, while underlying laws, such as gravity in cosmology and natural selection in biology, help guide the trajectory of evolution toward more organized states. Moreover, both cosmic and biological evolution involve processes of self-organization. In the cosmos, gravitational forces lead to the self-organization of stars and galaxies as matter clumps together under gravity, forming intricate structures. In biology, self-organization can be seen in the development of complex multicellular organisms from simpler cell aggregates, where individual cells come together to form tissues and systems through coordinated interactions. Both systems showcase how interactions among simpler components can lead to emergent properties that cannot be predicted from the components alone. Additionally, both realms demonstrate the concept of interdependence and interconnectedness. In the universe, galaxies interact gravitationally, influencing each other's evolution, while stars produce elements through nuclear fusion that become the building blocks for planets and eventually life itself. Similarly, in biological ecosystems, species coexist, compete, and cooperate, shaping each other's evolutionary paths. This interconnectedness highlights the importance of relationships and interactions in fostering complexity, whether in the cosmos or living systems. The parallels drawn between cosmic evolution and biological evolution underscore common themes of gradual change through incremental processes, the role of randomness, self-organization, and the interconnectedness of components. By exploring these similarities, we can gain a richer understanding of the underlying principles that govern both the universe and life, fostering interdisciplinary dialogue between cosmology and biology. Linguistic structures play a significant role in shaping our ability to discuss and theorize about complex concepts such as nothingness and the early universe. The way we formulate language not only reflects our thoughts, but also influences how we frame ideas and communicate abstract notions. This relationship between language and thought can profoundly affect our understanding of foundational cosmological ideas. One critical aspect is how the language we use can constrain or enable our conceptualizations of nothingness. In many languages, the term nothing is loaded with implications that may limit our ability to fully grasp the idea of a complete absence. For example, the use of negative constructions in sentences often draws on binary oppositions, such as something versus nothing, that can inadvertently anchor our thinking to a more dualistic understanding of existence. As a result, discussing nothingness becomes challenging, as our cognitive frameworks are often not designed to readily accommodate the absence of concepts. This limitation can impact philosophical and scientific discourse on the nature of the early universe, where ideas about vacuums or pre-Big Bang conditions are framed within existing linguistic structures. Additionally, the vocabulary available to discuss abstract concepts greatly influences the complexity of ideas that can be communicated. For example, rich terminologies in physics and cosmology allow scientists to express nuanced theories about the universe's origins, while the absence of similar terminology can hinder progress. The development of precise language for describing phenomena like quantum fluctuations or singularities can enhance our collective ability to engage with these ideas, encouraging further exploration of the early universe. Theoretical discoveries may be linked to how effectively such concepts are conveyed through language. Furthermore, linguistic structures can shape cultural perspectives on concepts like nothingness. Different languages and cultures may have unique approaches to discussing the void or the conditions that existed before creation. These culturally embedded linguistic frameworks can influence how societies perceive cosmological principles and even dictate the philosophical implications associated with the absence of existence. Such cultural perspectives play a role in guiding scientific inquiry and encouraging certain interpretations over others. Moreover, cognitive linguistics posits that the way we structure sentences can impact our thought processes. For example, languages that utilize metaphors, analogies, or spatial representations can influence how individuals formulate their understanding of abstract ideas. If the language encourages a narrative or framework that allows for flexible thinking about the origins of the universe, it may lead to more innovative theorizing. Conversely, rigid linguistic structures may inhibit novel approaches to discussing fundamental cosmic concepts. Linguistic structures significantly influence our ability to discuss and theorize about nothingness and the early universe. The limitations and richness of our language can shape conceptualizations, guide scientific discourse, and reflect cultural perspectives. By recognizing the interplay between language and thought, we can seek to develop more effective ways to articulate abstract ideas, ultimately enhancing our understanding of the fundamental nature of existence and the cosmos. Complexity theory provides valuable insights into our understanding of the universe's origins by examining how simple components can interact to give rise to intricate and emergent systems. This perspective emphasizes that the universe is not merely a collection of isolated elements, but rather a dynamic network where interconnections and interactions lead to the formation of complex structures over time. One key insight from complexity theory is the concept of emergence, which describes how new properties or patterns arise from the interactions of simpler elements. In the early universe, fundamental particles like quarks and electrons interacted according to the laws of physics, leading to the formation of atoms and, subsequently, stars and galaxies. By viewing the universe through the lens of emergence, we can better appreciate how simple initial conditions, shaped by physical laws, have evolved into the rich tapestry of structure we observe today. This perspective challenges reductionist approaches that seek to explain the universe solely by examining its individual components. Additionally, complexity theory highlights the importance of feedback loops and nonlinear dynamics in the evolution of systems. The universe's expansion from the Big Bang and the interactions between cosmic structures can be seen as complex systems that exhibit nonlinear behavior, where small changes in initial conditions can yield vastly different outcomes. This notion parallels ideas in chaotic systems, where predictability can be lost over time. Understanding these dynamics allows researchers to build more accurate models of cosmic evolution, encompassing everything from galaxy formation to the distribution of dark matter. Furthermore, complexity theory encourages interdisciplinary approaches to studying the universe's origins by incorporating aspects of sociology, biology, and computer science. This broad perspective can foster innovative methodologies, leading to new insights about how complex cosmic phenomena operate. For instance, studying the formation of large-scale structures in the universe can benefit from models originally developed in fields like ecology or network theory, where the principles of interconnected systems are similarly applicable. Another intriguing aspect of complexity theory is its emphasis on adaptability and resilience within systems. The universe has undergone various phases of evolution, from the formation of the first atoms after the Big Bang to the emergence of stars and galaxies. This adaptability can be seen in how structures have persisted and evolved despite changing conditions and cosmic events. Recognizing these characteristics in cosmic evolution may enhance our understanding of how life's resilience emerges in biological systems, leading to a more integrated view of nature. Complexity theory offers profound insights into the origins of the universe by emphasizing the roles of emergence, nonlinear dynamics, interconnections, and adaptability. By applying these principles, scientists can develop a deeper understanding of how the universe evolved from simple initial conditions into the complex and intricate cosmos we observe today, fostering interdisciplinary approaches that enhance our comprehension of both cosmic and biological phenomena. Concepts from computer science, particularly information theory, have intriguing applications in the realm of pre-Big Bang physics, providing frameworks to explore the nature of information, entropy, and the underlying order of the cosmos. These principles can enrich our understanding of the early universe and the conditions that may have existed before the Big Bang. One of the central applications of information theory in this context is the concept of entropy. In information theory, entropy measures the amount of uncertainty or information contained in a system. Similarly, in cosmology, entropy is a critical factor in understanding the early universe's state. Before the Big Bang, the universe is thought to have been in a highly uniform or low entropy condition, where matter and energy were evenly distributed. Understanding how information and entropy relate can help physicists explore how slight fluctuations in this uniform state could have given rise to the structures we observe today, including galaxies and cosmic filaments. Moreover, information theory underscores the importance of data transmission and storage, which can provide analogies for understanding the processes that occurred in the early universe. Just as information can be encoded and transferred in various systems, fundamental physical processes during the pre-Big Bang era may have involved the encoding of energy and matter in ways that set the stage for the universe's evolution. Exploring these ideas within the framework of information theory allows researchers to think critically about how energy and information were interrelated at this primordial stage, leading to discussions about the fundamental nature of reality itself. Additionally, concepts like the holographic principle, which suggest that the entire universe's information can be encoded on a lower dimensional boundary, can intersect with ideas from computer science. This principle implies a profound relationship between information and the physical structure of the universe. If the universe's information content is fundamentally linked to its geometry, then insights from computer science about data compression and encoding may offer valuable tools for understanding how complexity emerges from simpler components in cosmological contexts. Furthermore, in recent explorations of quantum mechanics, researchers have revealed interesting interconnections between quantum information theory and cosmology. The study of quantum entanglement, superposition, and the behavior of particles at a fundamental level can evoke notions of how information is processed within the fabric of the universe. This leads to questions about how information might have played a role in the transitions from pre-Big Bang states to a more complex universe. Information theory provides potent concepts that apply to pre-Big Bang physics by illuminating the relationships between entropy, data encoding, and the fundamental nature of the universe. By leveraging insights from computer science, physicists can further explore the intricate interconnections involving energy, matter, and information, ultimately deepening our understanding of the conditions that existed before the cosmos as we know it began. Sociology offers valuable insights into how scientific communities develop and accept theories of the early universe, emphasizing the social dynamics, cultural influences, and collaborative processes that shape scientific knowledge. Understanding these sociological factors can illuminate how theories evolve, gain traction, or face resistance within the scientific community. One crucial aspect is the role of social networks and collaboration in the development of scientific theories. Scientific discoveries often arise from collaborative efforts among researchers across disciplines. In the field of cosmology, the sharing of ideas and data among scientists can foster a more inclusive environment where various viewpoints are considered, allowing for a richer discourse surrounding theories of the early universe. Sociologists study how these networks facilitate communication, enabling researchers to build on each other's work, leading to the refinement and evolution of theories over time. Furthermore, the process of scientific consensus is shaped by sociological factors. The acceptance of new theories often requires the validation and endorsement of established experts and institutions within the scientific community. This need for peer validation can lead to the phenomenon of scientific gatekeeping, where certain theories gain prominence while others are sidelined based on social status or credentials of the proponents. Sociological research can help reveal how power dynamics and authority influence which theories are prioritized, shedding light on the mechanisms through which scientific communities negotiate consensus around complex ideas about the early universe. Cultural contexts also play a significant role in shaping how theories are developed and received. Scientific progress is not isolated from cultural beliefs and societal values, which can shape research priorities and influence funding decisions. In the case of theories about the early universe, the broader societal interest in understanding cosmic origins can drive funding and media attention, nurturing an environment where specific theories gain visibility. Understanding this interplay between culture and science can provide insights into how societal narratives can influence the acceptance of particular cosmological models. Moreover, sociology highlights the importance of public engagement and education in the development of scientific theories. The ways in which scientific ideas are communicated to the public can have a profound impact on their acceptance. Engaging the public with accessible narratives about the early universe can foster interest and understanding, which may, in turn, affect how scientific communities perceive the relevance of certain theories. Positive public reception can lead to increased funding and support for those areas of research, influencing which theories are further explored and accepted. Finally, the study of scientific revolutions, as proposed by sociologists and historian Thomas Kuhn, reveals how shifts in paradigms can lead to the acceptance of new theories. When existing frameworks encounter anomalies they cannot explain, such as new observations related to the early universe, scientific communities may undergo crises that prompt the re-evaluation of established ideas. Sociological analysis of historical shifts in thinking can help to identify the factors that contribute to paradigm changes, providing context for how today's theories may evolve in response to future discoveries. Sociology contributes essential insights into how scientific communities develop and accept theories of the early universe. By examining the roles of collaboration, consensus building, cultural contexts, public engagement, and paradigm shifts, we can gain a deeper understanding of the social dynamics at play in scientific inquiry and how they ultimately shape our comprehension of the cosmos. Economic models of resource distribution offer intriguing parallels to the distribution of matter and energy in the early universe, highlighting how both systems can be understood through principles of allocation, scarcity, and dynamics of growth and evolution. By examining the similarities in these processes, we can gain insights into how the universe evolved from a homogeneous state into the complex structures observed today. One of the fundamental concepts in economic models is the allocation of scarce resources, which directly relates to the distribution of matter and energy in the early universe. Shortly after the Big Bang, the universe was characterized by a near-uniform distribution of energy and matter. As the universe expanded and cooled, quantum fluctuations created variations that led to localized densities of matter. Similarly, in economic systems, the distribution of limited resources can give rise to inequalities and variations in access. The ways in which these resources are allocated can parallel how gravitational forces in the universe gather matter to form galaxies, stars, and planets, a reflection of more densely distributed resources within a larger framework that is expanding. Additionally, concepts such as market dynamics and competition can provide valuable analogies for cosmic processes. In economics, competition among agents drives innovation and improvements in efficiency, which can be compared to the competition among gravitational forces that shape the formation of structures in the universe. For example, areas with higher concentrations of matter may attract more mass, leading to the creation of complex systems such as galaxies. This competitive aspect parallels market forces in economics, where entities strive to optimize their positions in resource distribution, both leading to unequal but sometimes beneficial outcomes in the context of growth and stability. The process of feedback loops is another key concept shared between these fields. Economic models often illustrate how resource feedback, such as reinvestment or resource depletion, can influence future availability and distribution. In cosmology, the dynamics of matter and energy also demonstrate feedback mechanisms. For instance, the accumulation of matter into galaxies can enhance gravitational pull, attracting more matter and facilitating further growth. Understanding these feedback loops, whether in economic contexts or cosmic evolution, helps illustrate how small changes can lead to significant, sometimes unpredictable outcomes over time. Moreover, the study of entropy and thermodynamics, which frequently incorporates economic models to analyze resource distribution and scarcity, has parallels with cosmological processes. In economics, the second law of thermodynamics can help explain how systems evolved toward equilibrium, while in the early universe, as it expanded, the distribution of energy and matter increased entropy. As structures formed through gravitational clustering, the energy states of the universe transitioned, leading to a more organized distribution of matter, akin to an economy transitioning from a state of scarcity toward one of organization and stability. Economic models of resource distribution relate to the distribution of matter and energy in the early universe through concepts of allocation, competition, feedback mechanisms, and the evolution of systems over time. By recognizing these parallels, we can enhance our understanding of both economic systems and cosmic evolution, emphasizing how complex interactions can give rise to rich structures and dynamics in seemingly disparate fields. Music theory offers fascinating insights into the concepts of harmony and symmetry in the cosmos, revealing deeper connections between art and science. The principles of music, particularly those related to harmony, rhythms, and structures, can serve as analogies for understanding the relationships and patterns within the universe, enhancing our comprehension of cosmic phenomena. One of the key areas where music theory intersects with cosmology is through the concept of harmony. In music, harmony refers to the combination of different pitches or tones that create a pleasing sound or balance. Similarly, the universe exhibits harmonious relationships through the interactions of fundamental forces and particles. For example, the fundamental forces of nature, such as gravity, electromagnetism, and the nuclear forces, can be seen as a symphony of interactions that govern the behavior of matter and energy. Just as harmony in music is achieved through the careful arrangement of notes, the balance among these forces produces the intricate structure and behavior of the universe, leading to the formation of galaxies, stars, and even the conditions for life. Additionally, symmetry plays a crucial role in both music and the cosmos. In music, symmetry can be observed through patterns and repetition in melodies and harmonies, creating a sense of balance and coherence. In astronomy and physics, symmetry is a guiding principle that helps to describe the laws of nature. For instance, the conservation laws in physics, such as the conservation of momentum and energy, are often rooted in symmetrical properties. In particle physics, the symmetries associated with fundamental particles help dictate their interactions and behaviors at the quantum level. Understanding how these symmetries manifest in the cosmos can provide insights into the fundamental design of the universe itself, akin to how symmetry creates structure and form in musical compositions. Another area where music theory provides insight is through the use of scales and intervals. Musical scales, which consist of specific intervals between notes, establish a framework for creating melodies and harmonies. In a similar vein, the relationships between different physical quantities in the universe, such as time, space, and energy, can be viewed as a kind of scale. For instance, the concepts of redshift and blueshift in light from distant galaxies can be likened to musical intervals that convey movement and change. This analogy emphasizes the interplay between frequency and energy in both sound and light, enhancing our understanding of phenomena like gravitational waves and cosmic expansion. Moreover, the use of rhythm in music can be paralleled with the cyclical patterns observed in cosmic phenomena. Celestial bodies, such as planets and stars, exhibit rhythmic behavior through their orbits, often reflecting predictable patterns due to gravitational interactions. This cyclical behavior can be likened to rhythmic patterns in music, where beats and measures produce a sense of order and predictability. Recognizing these rhythmic patterns in the universe aids our comprehension of complex systems and the dynamics that govern them. Insights from music theory regarding harmony, symmetry, scales, and rhythm can deepen our understanding of the cosmos. By drawing parallels between the structured beauty of music and the intricate order of the universe, we can appreciate the underlying principles that govern both realms, enriching our perception of existence and the relationships that bind us to the cosmos.